Yeah, okay, everything works. So we're about to start our morning session, which is dedicated to ion implantation, modification, and surface analysis. I'm Platon Karasel from St. Petersburg Polytechnic University, and I will chair part of this session together with Vladimir Papov from Novosibirsk Institute for Semiconductor Physics. And we have some changes in program, unfortunately. Mr. Shankar Dutt has withdrawn his talk. So in the first part of our session, we will have a substitution with Alena Nikolskaya. And also some changes should happen in the second part of our morning session. But the first talk, which should be delivered by Daniela Gogogova from Bulgaria, devoted to gallium oxide, a promising material for the next generation high-power electronics, should be presented online. Daniela, do you hear me?
Yes, Professor Karasel.
So
thank you very much for your introduction.
Please proceed. We see your slide, but not in full screen mode. Full screen, please, Daniela. Switch to full screen mode.
Oh, sorry.
Press F5. F5.
One moment.
Yeah. And slideshow from left button. Yeah. Okay.
Okay. Sorry.
Okay. Yes. Please start.
So the title of my talk, as already announced, is Gallium Oxide, a promising material for the next generation high-power electronics. I will focus on material aspects of this problem. So after a short introduction, I will shortly mention the methods for growth of bulk epitaxial gallium oxide and will present our new concept for epitaxial growth by MOVP of beta gallium oxide, the fact studies and conclusions. So why do we need to develop gallium oxide and its different polytypes if trinitrides and silicon carbide are so well developed and almost everything could be done, all devices for wide band gap semiconductors could be fabricated. Beta gallium oxide was rediscovered about 10 years ago as a new transparent semiconducting oxide because it has ultra wideband gap of 4.85 EV, and this means it's optical transparent up to the middle ultraviolet range, and UVC range is especially promising in medicine and for different short wavelength photonic devices, as well for solar blind Schottky photodiodes and in transparent electronics. The second reason for the huge interest in studying gallium oxide, and especially its thermodynamically stable beta phase, is that it has high breakdown voltage, which is superior in comparison to trinitrides and 4H silicon carbide. Here you can see shortly summarized in a table the advantages of beta gallium oxide in comparison to the classical semiconductor silicon, which is not wide bandgap semiconductor, and the other wide bandgap semiconductors. The reason number 3 for the huge interest in beta gallium oxide is the availability of low-cost melt growth methods for production of oxide crystals. First was Czochralski, nowadays done in Germany and Japan, float zone in Japan, edge-defined film fat growth method, Japan and China, and HVP growth mode developed in Russia and Yoffe Institute and as well in Japan. So other reasons for the huge interest in gallium oxide polymorphs is that the beta gallium oxide has very large Ballinger figures of merit, as well as high breakdown field effect larger than the 3 nitrides. Meanwhile, from growth aspects, there is no formation of a second phase, as in the case of ingon when alloying with indium. Moreover, gallium oxide has radiation hardness better than 3 nitrides. For example, I would recommend the papers of Professor Karasyanov and Titov in vacuum for demonstrating that gallium oxide polymers have better radiation tolerance or hardness than the well-developed, from technological point of view, gallium nitride. Also, 2 interesting papers by the group of Alexei Mikhailov and Professor Teitelbaum from Nizhny Novgorod University are published in Materials Letter and the review paper in Journal of Vacuum Science. So here you can see a bit older, since 2020, power electronic technology roadmap. And here you can see that it is expected within 8 years, ultra-wide bandgap semiconductors like beta gallium oxide to be much better developed and included in fabricated devices. So actually, ultra-wide bandgap semiconductors are the key to smart power grids, for which we are listening so much in media, and it is written in scientific newspapers, because with the inherent properties of wide bandgap semiconductors, energy could be saved, energy in not simply in generation, but in transmission and distribution, because when you consume huge amount of energy, the loss at the moment are really large. Here I wish shortly to mention the physical properties of gallium oxide. It has several polytypes, even new are recently discovered. The thermodynamically stable is beta gallium oxide. This is the high temperature, and as not expected to, like in the nature, it is not hexagonal like alpha low temperature phase, but it has monoclinic structure that is a bit complicated, and during the growth leads to formation of stacking faults and other type of defects. You see that the alpha modification or polytype has a bit larger bandgap, and it's more convenient to be grown on hexagonal substrates. Sorry. The huge problem with gallium oxide, it's low thermal conductivity for semiconductor. So people should make thermal conductivity management in order to make devices that are good, that have good functionality. Another disadvantage of this material is that p-type doping is not reliable. There are some publications, but they were not confirmed by the audience. However, it is not so huge limitation because unipower devices could be grown. The methods for epitaxial growth of gallium oxide are MB. It was the first method. However, it's state-of-the-art, produced state-of-the-art, the best quality material. It's carbon-free, but it's not for industrial production. Then PLD appear for oxide. It has certain flexibility in composition variation when tuning the band gap depending on the requirements. The MLCVD or meta-organic vapor phase epitaxy, the first report was of Fujita in Japan, growing directly on sapphire alpha phase, but it's a low temperature phase and above 550 degrees C. It transforms to thermodynamically stable beta phase. Atomic layer deposition is also one. This is the time resolved CVD actually, and could be used for growth of conformal thin films on large areas with large growth rates, however, using organic precursors that contaminate with carbon. Here could be added the inorganic MOCVD. This is actually hydride vapor phase epitaxy used at the Joffe Institute. We have developed a new method for epitaxial growth of beta gallium oxide at Linköping University. It's actually an old concept, the hot wall concept, used for growth originally of silicon carbide and later on for growth of 3 nitrides. This method provides uniform heating of a large area. The whole growth area has the same temperatures. So this means that we provide more efficient cracking of the precursors of metal organics and oxygen precursor. We are able to cover up to 2-inch wafers very homogeneously. And for silicon carbide and 3 nitrides, my colleagues at Linköping University using this approach have reached superior performance of silicon carbide and 3 nitride devices because they have provided ultra high purity of the layers, epitaxial layers grown. In our case, we had to modify one old silicon carbide reactor and to make it, to adopt it for beta gallium oxide epitaxy. For this purpose, we are using gas foil rotation to have uniform deposition. Our susceptor is silicon carbide cover to prevent decomposition of heaters, and of course the insulation cannot be covered by this. We have water-cooled injector with isolated injection of different precursors. We are able to alloy with aluminum and indium and grow layers on 2-inch. The temperature range is large, so we would be able to grow even the alpha or some other polytypes. And for gallium source, so far we use trimethyl gallium. This is not the best organic precursor from point of view of purity, because it incorporates in the layers more higher carbon concentrations than other meta-organic precursors. However, it provides larger growth rates, what is also an important issue when you need to grow several micrometers layers. So we have worked in two different regimes, high pressure and low pressure, and we established the best conditions within this base pressure values, and the growth rate could be up to 1 microns per hour. The temperature in the hot wall process is much lower, actually with 100 degrees lower than in the cold wall reactors that people are using all over the world, and I have used at XXVI Berlin. So when buying substrates, we bought them from Novo Crystal Technology Company. The producers say they are epi-ready. However, the surface of gallium oxide substrates with orientation 010, -201, and 001 look like this. Obviously, they are not epi-ready. So typically in epitaxy of oxide, people are using annealing at the temperature of about 1000 degrees C for 1 hour. However, we have developed one cost-effective process, annealing in situ in reactor in low pressure argon for this different surface orientation. And the most attractive and cost-effective method was annealing in oven in argon at high pressure, 900 millibar. For this annealing was performed just for 1 minute compared to typically annealings at 1000 degrees for 1 hour. We have one cost-effective process, and the results are almost same. Here you could see the formation of a step. In the case of -201, we have a large step, result of step bunching. And when growing by homoepitaxy, these are the results for different crystal surface orientations. These are 2θ omega scan, and you see in the case of 010 orientation, one single peak corresponding to the substrate. In the case of -201 and 001, we have, because of the symmetry, this break orientations. Here, the rocking curve scans of high-resolution XRD are shown for the substrate and epitaxial layer. And you could see, especially for these surface orientations, 001 and 010, the FWHM of the epitaxial layers is almost like of the melt-grown substrate. This is really a good result because substrates are grown at thermodynamically stable conditions. So by hot wall RCVD, we were able to grow close to thermodynamical equilibrium and get crystalline quality that is comparable to this of bulk substrate. Meantime, here you could see the RMS values are also good. Since the group in Linköping University are expert in ellipsometry and different more advanced ellipsometry-based techniques. By optical Hall effect, they have determined these mobility values for different orientation, mu A, B, and C. And they compare very well with the results of electrical Hall effect. This high free carrier concentration is a technical problem because we need second dilution of our silane precursor for silicon doping. It could be solved very soon. So when putting our data for mobility in this graph from the publication of Mankato and Crystal Growth and Design, for high doping, for high doped samples, we get even better results than in the cold wall reactors and other methods like HVP and so on. The electron mobility in our case is among the best values in the literature, and the roughness of 0.8 nanometer over 10 per 10 micrometer is a record value for showing the smoothest surface published in the literature. So my colleagues investigate by optical EPR different effects. This is in the terahertz range. Unfortunately, I am not expert in this, but this is really a very good technique, and in future we could collaborate on this. In conclusion, a new hot wall approach to the emulsivity growth of epitaxial beta gallium oxide at reduced temperature and reagent flows, keeping the high growth rates and using primitive gallium precursor is demonstrated. This method delivers state-of-the-art homoepitaxial beta gallium oxide material, and the newly developed hot wall emulsivity gallium oxide reactor concept offers a versatile method with the potential for cost-effective, industry-relevant growth. Thank you very much for your attention.
Thank you, Daniela, for a very interesting talk. Now it is open for discussion. Yes, we have questions in the audience, please.
Oh. Okay, thank you for interesting talk. I missed in your talk what is the motivation to study homoepitaxial growth. From some point of view, you already have a good quality substrate, and you can use it for electronic application. Why do you need homoepitaxial thin film on top of it?
It's a general question. In principle, substrates are more expensive than epitaxially grown layers. Therefore, to make devices, we need several heterostructure junction or other type transistors. Therefore, you use the substrate just to hold the structure, and it is not needed to introduce functionality in the devices because the substrates are expensive in general.
So from this point of view, you need to use heteroepitaxy to study heteroepitaxy.
Well, when growing by heteroepitaxy, such monoclinic structure, you get many defects because the gallium atoms could have different hexagonal, different orientation which makes many stacking faults, like in the beginning of silicon carbide growth. You remember in this case, I have worked in 3 nitrides in the growth first of bulk, and it was minimum 25 years since the people were able to grow high quality substrate by vapor phase method or solution growth. So first of all, we need substrates that have a very low concentration of dislocations and point defects that are not so, but epitaxial layers can repeat the structure. And when you grow monoclinic on hexagon, when you grow monoclinic beta gallium oxide on sapphire, you get a huge amount of defects. Of course, depending on the application, it could be done. For example, for electronic devices, it's needed to have homoepitaxy. For some optical application, it's good to use heteroepitaxy.
Okay, thank you.
Then we could live with defects, especially in the case of nitrides. The laser diodes based on gallium nitride were able to work at so high defect density, like 10 to 9, 10 to 10 per square centimeter. It was ridiculous, but it's not with all materials like that.
Thank you very much.
Daniela, thank you very much. You go to the next question.
Thank you very much to the organizers for their kind invitation for me. And I hope next time we meet in person.
I hope so, but we have one more question to you yet.
Yeah? Okay.
Daniela, Vladimir Popov, Novosibirsk. What kind of power devices can you suggest for your excellent materials? I mean, this is a simple diode, or this is a field effect transistor, but in the case of field effect transistor, you should have some dielectric with very nice properties, or using some kind of heat sink, because your conductivity is 1 order of magnitude lower than in the case of silicon.
Yes, thank you very much for this professional question. I do understand you perfectly. However, I am a grower. So my task is to provide the best material I can, but there are some other device people that are providing all this. They have facilities to grow devices and make this heat management. In the beginning, I was also surprised, why do we need to study gallium oxide if the thermal conductivity of sapphire is even higher than of gallium oxide? But it's ridiculous that people find such tricks, some tricks to avoid this problem. And one of them is, for example, to make the substrate very thin, extremely thin.
Okay, thank you very much.
So it has not so huge influence on the heteroepitaxial structure grown on it.
Okay, so then Daniela, thank you again for that very nice talk. Do we have other questions? David Isakovich, please. David Tetelbaum.
Nice to see you.
Thank you for a very interesting report. And what the defects prevail in your best films? The extended defects or point defects?
So at the moment, because we are growing in silicon carbide covered growth zone, and oxygen is rather aggressive to this material, So we have carbon incorporation that should be decreased by using different type of insulation and covering by boron nitride, the growth parts. Or actually, I show you this rocking curve spectra. If the substrate, which has defects about 10 to minus 4, 10 to 4 per square centimeter or less, and we have the same FWHM of the rocking curve, this means we have the same dislocation density like the substrate.
And what type of substrate you have used? Is it Tamura or other?
No. Let me look again. In the beginning, we were using Tamura, but here we have novel crystal technology, Inc.
But it is the same Tamura.
Okay. Sorry, I'm not.
Okay, so thank you very much for the nice talk, and we are really happy to see you not in person, and hope to see you in person
Next time.
Yeah. Thanks. Thank you again. Let's thank the speaker again.
Thank you so much for invitation.
And we proceed to the next talk. It should be it should come from China by Professor Guanghua Du. Is he online? I'm not sure. Professor Du, are you online? Well, I don't see him. And technical staff can help us with this. Then, okay, what can we do? Then we proceed to the next talk, which also should come from China by Professor Chen De-Yang. Is he online? Okay. Chen De-Yang, are you online? Again, no. Well, I think that something happened to internet in China. Okay, then, as of announced changes, in this case, we proceed to the next talk, which should be delivered by Alena Nikolskaya. And it is talk from the audience. Alena, please.
So, good day. I will talk today about the structure of silicon dioxide and silicon systems related with different ions. And today I will pay more attention to the structure of these materials and just mention a bit about luminescence properties of this system. So silicon is well-known semiconductor, which has been used for many years in electronics. But following Moore's law directly, we have some problems fundamental, like limitation of transmission speed of information in circuits, which used for this electronic signal from element to element. So we need to find new approaches which go beyond the Moore's law. One of the most best approach to overcome this problem is the use of ion implantation to modify properties of silicon. For example, fast transformation can occur in silicon during ion implantation. Ion synthesis of various polytypes of silicon would allow to create silicon-based gate structures with which enhance its functionality. The ion implantation also can used to control the optical properties of silicon by forming light-emitting defects in it. The structures obtained by ion implantation can be used both in classical optoelectronics and as photonic qubits in quantum mechanical photonic devices, for example. But both approaches mentioned above has their own drawbacks. For fast transformation, it is lack of technology development and insufficient knowledge about the mechanism of formation hexagonal polytypes. For defects engineering, it is low temperature stability of light-emitting defects and strong temperature quenching of their luminescence. Overcoming this problem with significantly enhance functionality of electronics and optoelectronics in the future. Earlier, during the synthesis of gallium nitride nanocrystals in silicon dioxide matrix, we investigate that additionally to these nanocrystals, some inclusions of hexagonal silicon of 9Fs were formed in substrate of silicon at the interface with silicon dioxide. Such inclusions can be characterized as periodic sequence of twinning defects, which indicates the hexagonalization of silicon. Hexagonal silicon polytypes differ from each other by a sequence of arrangement close-packed planes. If for cubic silicon, this sequence is ABC, ABC. So for hexagonal silicon, it is AB, AB. And for 9Fs, which we have studied, it is a more complicated sequence, which you can see on the slide. The formation of 9Fs was detected by us by periodicity of atomic planes and the presence of additional reflection on the Fourier transform patterns. According to the SRIM code, we found that under implantation conditions we used in silicon substrate at the interface with silicon dioxide, a xenomorphous layer formed with thickness of about 30 nanometers, which is quite close to the thin of layer which contains 9R inclusions. So we supposed that the formation of 9Fs occurs under solid phase epitaxy during high temperature annealing. The use of chemically active ions as gallium provides additional complication to the interpretation of our results. So in the further, we used inert gas of krypton as irradiated ions. We also used silicon dioxide silicon substrate systems for this irradiation and the same annealing parameters. According to the SRIM calculation, the main projected range of krypton ions is slightly less than for the gallium ions. So we had to reduce silicon dioxide film thickness to 120 nanometers to reproduce the same conditions which were used for gallium ions. According to the transmission electron microscopy data, the thin amorphous layer form in silicon substrate at the interface with silicon dioxide, which thickness is about 25 nanometers. After high temperature annealing, this amorphous layer recrystallized with formation of inclusions of 9 Fs. According to the literature data, hexanal polytypes are formed under extremal conditions. For example, under influence of mechanical stresses. In our case, mechanical stresses can arise in silicon substrate and during solid phase epitaxy under following factors, like a large gradient of secondary defects at vacancy in interstitial complex due to radiation through silicon dioxide film, the presence of silicon oxide bonds in the amorphous layer, and due to the difference coefficient of thermal expansion for silicon dioxide film and silicon. Another important factor in the effectiveness of dexionization of silicon was orientation of surface of the silicon. Under equal conditions, the main factor which influenced the formation of hexanal phase is angle between lateral force of a vector which presents under the mechanical stresses and angle between close packed planes 111 in silicon. So for considered above plane 100, this angle is 54 degrees. It's the most great angle, so only inclusions of 9 Fs are formed. And for the orientation 111, this angle is 1 degree. So the hexanalization was fully on all, almost on all layer of substrate. In this work, the band structure of the 9 Fs was for the firstly calculated. It turned out that 9 Fs is indirect semiconductors with direct band, with indirect band about 1 eV. The investigation of the luminescence properties of synthesized samples which contained 9 Fs showed the luminescence line and at 1240 nanometers, which is intense up to temperature of liquid nitrogen. The position of this line is quite close to the forbidden band gap of 9 Fs. So we have suggested that this line is according to the emission from this phase. However, laying by laying etching, chemical etching of silicon showed that the maximum intensity of this line is achieved in a deeper layer than region which contains 9 Fs. So we put forward new interpretation for this line. Quite close in spectral position for the the line found by us is well-known line W line, which arise in photoluminescence specters when silicon is irradiated with various ions, electrons, and neutrons. And according to the modern view, this emitted by named 3 interstitials of silicon. It's 3 interstitials in silicon. But the properties of this line are different from us, from line found by us. So for the W centers, the maximum intensity is rising at annealing temperature about 270 Celsius degrees, and almost full quenching is about 500 Celsius degrees. For us, for our line, its maximum intensity achieved at 800 Celsius degrees, and the luminescent questioning occurs at higher management temperature. We suggest that this our line at 1240 nanometers has the same emitting defects, E3 defects, but with different properties from W centers according to the different defect environment. When we irradiate silicon through the silicon dioxide film, we have more pronounced separation between interstitials and which are building material for the E3 defects, and vacancy which can recombine with interstitials and destroy our light emitting centers. So as we can see from the distribution of primary defects and depths, it can be seen that in our case, implantation through the film, this separation is more pronounced. And the classical case, when we irradiate silicon substrate directly, we have a lot of vacancies close to our interstitials. So most of them can't survive till high temperature annealing. So we have studied 9 AFAS, which form under ion radiation of silicon dioxide silicon systems. Also, we found that the efficiency of dexionalization is depends from surface orientation of silicon. Also, we supposed the mechanism of formation of this phase during solid phase epitaxy. And we found a new photoluminescence line at 1240 nanometers. Thank you for your attention.
Thank you very much for nice presentation. And this presentation is open for these questions. Please, your questions. Okay.
Спасибо, очень хороший доклад. Я хотел такой наивный вопрос. Почему вы выбрали криптон для облучения? Это большой тяжелый атом. Соответственно, он недалеко пробегает и делает большие повреждения. Почему вы выбрали криптон?
Ну, как я уже сказала, впервые мы обнаружили формирование наших включений, когда мы облучали оксид кремния на кремний ионами галлия, а криптон как раз близок по массе к галлию, поэтому мы ожидали такие же свойства при облучении. Но мы использовали и другие инертные газы, но криптон, как казалось, был лучший выбор.
Хорошо, спасибо.
Please, more questions. Is there a question online or not? Do you see the question online? No. Okay, I have more question. Alina, did you try to use different kinds of dielectrics? I mean, alumina or maybe nitride of alumina or silicon to exclude the existence of oxygen in your layers and the participant in the formation of your luminescence defect?
Yes, we have used different films, but we investigate that the presence of oxygen is necessary for formation of our inclusions and our luminescent centers.
Okay, thank you. More questions? Okay, thank you again. And the next talk of our session is the invited talk of Professor Platon Karasov, and the title is где он здесь? Okay, thanks. Okay. Radiation damage accumulation in alpha. alpha gallium oxide under KeV ion bombardment. Please, 25 minutes with the questions. Okay.
Thank you very much for invitation. And is it work? Okay. So I now get all you back to the gallium oxide topic, which is of great interest. And thanks to Daniela, I can omit some words about its very nice properties. But first of all, I have to introduce you our team, which is from St. Petersburg Polytechnic University, our students, PhD students, and group of Vladimir Nikolaev from UFE Institute and Perfect Crystals LLC, who has grown these samples, which we used for our investigations. This is the outline of my talk. First, I will say a few words about the motivation behind our investigations. Then I will show you experimental details of our investigations, and then I will discuss low dose damage formation, then how those high dose effects, dose rate effects, and then I'll come to the conclusions. First of all, motivation, as Daniela already told us, gallium oxide is a wide band gap semiconductor with a pretty high band gap from 4.5 to 5.3 electron volt, depending on the polymorph, and this high band gap value causes high breakdown field. And indeed, I have to show you this Baliga figure of merit, which proves that gallium oxide is very promising material for high power electronics. And indeed, which is of great interest for us, that it crystallizes into a number of polymorphs. I have shown here 4 of them, and most important are alpha and beta phases. And indeed, beta phase has attracted a lot of research, as Daniela told us. Good quality samples could be easily grown, and even bulk samples from melt, like each film fed grows and floating zone grows in large size. But alpha gallium oxide has also has even larger band gap, and nowadays it is proved to be stable at atmospheric pressure up to 550 degrees Celsius, and indeed it could be epitaxially grown by mist, CVD, HVVP, and some other techniques on sapphire substrate, and it grows epitaxially with a very low lattice disorders, so high quality epitaxial film could be obtained. And on the other hand, radiation damage accumulation in gallium oxide is still in its infancy, and this is especially true for alpha polymorph, as the good quality crystalline films are were obtained not so far ago. Our samples were alpha gallium oxide, HVP grown on C-place sapphire without any intentional doping, so it were insulators. Irradiation were done 70 degrees of the O1 direction at room temperature in a wide range of ions. As you can see, we use fluorine, phosphorus, xenon, and tantalum, which let us investigate the effect of ion mass. Also, we have used molecular PF4 ions, which let us investigate the effect of collision cascade density, and the energies, which I show you here, let us to get primary point defect generation at almost same depth, so we have no effect of the primary of the depth of the defect generation, and ion beam currents were chosen in order to keep primary defect generation rate the same. So we investigate only the influence of ion mass or collision cascade density in this case. Then analysis which we used, indeed it was X-ray diffraction for the version samples, then Rutherford backscattering in channeling mode in order to investigate damage created by irradiation, X-ray photoelectron spectroscopy, and atomic force microscopy in semi-contact mode to investigate effect of radiation on the roughness of the surface. I have to show you this slide. It is the reactor where our samples were grown at atmospheric pressure with the growth rate from 0.5 to 10 micrometer per hour. And indeed, you can communicate to me or to Vladimir Nikolaev to make some investigation on the growth techniques. Well, initial sample, XRD shows the lines from sapphire, very nice lines from alpha gallium oxide, and weak lines from epsilon phase. Also, the good crystalline quality is proved by RBS in channeling mode. You see that the version spectra is very low in this case, and also, you can see in XPS spectra that only line of gallium oxide is present. So we have epitaxial gallium oxide film of a good crystalline quality as an initial sample. Then we performed ion irradiations. We start with monatomic ion irradiations, and this is P. You can see a set of RBS spectra for doses from 0.15 dPa to 5.4 dPa. Then these spectra were the distribution of damage were derived from the spectra, and in the next part of my talk, I will mostly show you only this disorder distribution instead of RBS spectra. What can we see in this disorder distribution? We see that damage is created in two peaks, one situated at the sample surface and another one in the sample bulk. And then bulk defect peak is situated deeper than maximum of ballistically generated point defects, and even deeper than projected range of implanted ions. Then we can see that damage saturates at 90% of total amorphization. Then we switch to lighter ions, fluorine ions. The depth of point defect generation is the same, number of point defect generation is the same again, but stay stable. The damage produced by fluorine ions is quite lower, as you can see here on the right panel of this slide. Again, we see bimodal damage distribution, and light ions are less effective in damage formation. Then we switch to heavier xenon ions. Well, surprisingly, some marks disappeared from the figures, but I have to note that in this case, when we use heavy xenon ions, amorphization is reached at the dose of 3 dPa. Again, we see bimodal depth distribution, and what is very surprising that bulk defect peak is even lower in the case of heavy ion than it was for the light fluorine or phosphorus ions. Okay. Then we try to investigate the effect of molecular ion irradiation. It is the effect of local increase of collision cascade density at the sample surface. You might recall that when the molecule impinged the target, individual collision cascade produced by its constituents overlap in the region close to the surface, and then they split, and overall cascade density decreases. And what do we see? That surface bulk peak is more pronounced in the case of molecular ion radiation compared to the bulk peak produced by monatomic phosphorus ions, but bulk peak saturates at the level of about 0.25, and no surface amorphization is seen in this case. Okay, so how can we explain this effect? This is the effect of collision cascade density. We have proposed the way to calculate this density in the paper cited here below, and you can see that collision cascade density for PF4 ions at close to the surface is higher than that for pure P ions, and exactly at the same depths, that depth range up to say 15 to 20 nanometers, PF4 molecular ions are more effective in damage production, as revealed by the left panel. So collision cascade density strongly affects damage formation, and cascade overlapping causes enhancement in surface damage layer formation. And on that slide, we compare the result of all irradiation performed to, as I call during this talk, to low doses. And we can see that the heavier ion is, the higher surface then damage is. And on the other hand, we have a very weak bulk peak. So we can conclude that the intrinsic point defects in gallium oxide are extremely mobile. And we can find the nonlinear effect of the cascade density on the damage production, at least in the surface damage layer. If we compare the results of irradiation of gallium and of alpha and beta polymorphs of gallium oxide, then we can conclude that the doses needed to reach the same value of that damage. You see that the damage on the left and right panels are almost same, but the doses in the case of alpha gallium oxide are pretty higher. For example, to reach say some saturation, you need 5.4 dPa in alpha polymorph and only 1.16 in beta polymorph. But indeed, bulk maximums and indeed damage saturates at 90% in both cases, and disordered depth profiles are different, and alpha polymorph is more radiation resistant than beta polymorph. Well, now we turn to the dose rate effect, because of it is well known that the rate of damage, primary damage generation, primary point defect generation rate may affect stable damage production. And in recent work published by Alexander Azarov and the group of Andrei Kuznetsov, we see that in the case of nickel ion irradiation, that temperature as shows panel A, and indeed ion beam current as shown in panel B, plays crucial role on the effectiveness of damage product production, especially at the sample surface. With the temperature increase, damage produced decreases, and the surface peak increases with the ion beam current increase. In our case, we used irradiation with phosphorus and molecular PFO ions, and in both cases, some small increase in the amount of the damage at the sample surface could be seen at a high ion beam current. And our beam current is slightly lower than that used by Alexander Hazarov. So unfortunately, we cannot proceed further with this experiment because of our implanter cannot give us higher values of beam currents. But in all this case, increase in the surface damage layer thickness is seen at high dose rate, and the high defect mobility in gallium sublattice is the main reason which can help us explain the effect seen. When we switched to even higher doses, we used doses up to 445 displacement per atom, which is pretty high. It means that each atom at the depth of the maximum of nuclear energy loss have been moved from its place 45 times. But even in this case, for the irradiation performed by phosphorus and PF4 molecules, no final amorphization is seen. You can see that in the RBS spectra, the channel spectra of P and PF4 cases are not reach random values. On the contrary, irradiation with 150 keV tantal ions gives us full amorphization, and in addition, we can see that some peak appears at the surface on the channel spectra after tantal irradiation. This is caused by implanted tantal ions, as was stimulated by ramp simulations. You can see that in the case of implantation up to 45 dPa, concentration of implanted tantal ions is quite enough to produce this additional surface peak. Okay, and what has happened in the case of nickel ions? You can see that irradiation to a dose up to 53 dPa, as published by Alexander Azarov, also let us achieve full amorphization in alpha gallium oxide. So this means that ion mass plays very important role in the process of total amorphization in this polymorph. Then another interesting feature which we observed earlier in gallium nitride. Just to recall you, I showed this old IFM atomic force microscopy scans for gallium nitride obtained after irradiation to a dose of 440 dPa with phosphorus and PF4 molecular ions. And you can see that some very nice structure is formed in the irradiated area. In addition, the step appears at the boundary of the irradiated and unirradiated area. Indeed, it is not quite straightforward in this case, but irradiated area is on the right hand for the upper case, and the irradiated is on the left hand in the lower case. And indeed, roughness increases with the ion dose, and the step height, we can see swelling or reduction in the implanted layer, depending on the ion specially used for irradiation. And we try to do the same for the alpha gallium oxide. And what do we see? First of all, we see that roughness of the virgin film, that the virgin film is not as flat as gallium oxide was. We see traces of grains, and we see some atomic steps. Irradiation to 45 dPa in all these three cases, ion dose is the same of 45 displacements per atom, and it smoothes atomic steps but has no effect on film grains. What about step between irradiated and virgin area? Up to 30 dPa, we have no effect on the irradiated layer thickness. And when we irradiate to 45 dPa, we see a small swelling in all cases. And swelling value is about 5 nanometer, almost independently of the ion species used. So what causes these effects? And indeed, when we implant to so high doses, some sputtering must occur, but we see swelling. So we performed XPS investigations of our samples, and for pure gallium oxide, we see seen in the virgin sample, some decomposition appears after high dose irradiation, and gallium appears after a high dose irradiation. And this let us explain that the structure changes. Now I come to the conclusions. We have investigated KV-induced radiation damage in alpha polymorph of gallium oxide, proved that it is more radiation resistant than thermodynamically stable beta polymorph. Gallium sublattice defects are very mobile in alpha gallium oxide. Cascade density enhance. Cascade density plays a very important role in damage generation. And ion irradiation up to 45 dPa has no weak on the has a weak effect on the surface morphology, and material decomposition is found in the irradiated layer. And now I thank you for your attention.
Thank you very much for a nice presentation, and this report is open for the questions. Please, the first one.
Thank you for the interesting talk, and I have a question about some structural properties. Do you have some data of structural properties of your samples, especially for the high doses, like 40 dPa and something 45? I think there are some strong, maybe new phases. Do you have some XRD data?
You mean XRD now?
TEM?
Not yet.
We
are working on that.
Displacement, yeah?
Well, we have RBS, but it shows us, of course, very disordered layers, but we do not know what if there are new phases or not.
What do you think about the formation of new phases in your samples after the radiation with such high doses?
Well, I know that Alexander Azarov has just published new work in Nature Communications suggesting formation of new phase, but I'm not sure if it is seen in our case.
Okay. Thank you.
We'll do this measurement indeed. Yeah.
The next question, please. Yes.
This is very interesting report, but I have two main question. The first question: why the iron is behave another than xenon? And second question: why the surface peak is higher than back peak? It is amorphous, and back peak don't appear the amorphous state.
I'm sorry, that David's question. What was the first question?
The first question: why the iron behave not so as xenon?
What iron?
This is a chemical effect, or
What kind of ions?
What kind of iron behaves differently than this xenon?
this I see that the iron is
Nickel.
For
Okay.
the level of defects achieve the amorphous state, and for
Yes.
xenon it is not.
It is. For xenon, it is. I'll show you.
The iron.
Here at 3 dpa, it is amorphous. Unfortunately, I'm really so sorry, but at this slide, the ticks disappeared. But on the left panel, you see.
Sorry, the iron, not the phosphorus. The iron. Ion.
I haven't. I haven't used iron. I have nickel.
Nickel.
I have nickel. And it is not my experiment. It was done by Alexander Azarov.
Oh,
This is the xenon, and it amorphizes. PF4 does not amorphize. P does not amorphize, but nickel amorphizes at very high doses at the surface. Why? Regarding the question why the damage forms as the surface, I can only give the explanation that the point defects are extremely mobile in the alpha gallium oxide, and they look for a sinks, and the surface is a very good sink for them, and the stable damage formation starts there, whereas maybe no traps are present in the bulk of the gallium oxide. And indeed, if you take a look then onto the for example, that slide, you can see that the damage is formed quite far from stable damage. Is formed quite far from the place where the point defects are generated.
thank you.
Okay. More question?
Thank you for a nice talk. I have two questions about the global practical motivation of your research for industry. You emphasize in your study on the structural defects, but usually when talking about the radiation effects in semiconductors, the major radiation factor is the charge redistribution in the semiconductor device, and are you going to investigate these effects as well? And the second question is about the selected radiation type. It's also about its practical motivation, because there are different radiation factors, for example, space radiation factors, artificial factors, and 100 TeV ions seems not to be usual radiation factor for the operation of the semiconductor devices. Thank you.
Okay.
But this is not regarding operation. This is about production of the devices, because of ion implantation is very important tool for the production of electronic devices. And in the case you want to produce, say, selectively doped areas or some insulative areas, you have to irradiate them with the keV energies. And then you have to understand how the damage produced should be removed, or how to produce damage which should persist in the case of in the case you need this damage for, say, for high resistant areas. And regarding the ion species, they are model ions indeed, just to model ion radiation effects. Then regarding the last part of your question, indeed we plan this research, but it should be done with some other ion species and energies indeed, of course.
Okay,
Thank you. Yeah.
And, more question? Yes.
Once again, thank you for very informative report. And please show slide number 12.
Number
12.
12?
Right.
The previous.
Oh, is it this one?
This one.
This one. And
Okay.
also in other cases.
Please, microphone.
Sorry.
Yeah.
I see that with increasing of dPA, maximum of the spectra is shifted to the bigger depths. Why it's so?
You mean on the right side?
Right, in both these cases, you see this maximum is shifted to the bigger depths when you increase this dPA.
With increasing fluence, do you mean?
No, this one. And also,
I think this is due to increase in the damage layer width. So you have to take into account that this is the result of RBS measurement, and in this case we have also work function of the machine, and when the damage layer width increases, it should be seen here first as the growth of the peak, and then of its widening.
as I understand, this maximum is correlated with level of disorder, right? And if you increase,
not directly, because of it is of course level of this. Okay, we can discuss it.
The relative disorder increases at the bigger depths.
Oh, it's the usual situation.
Number of irradiated particles.
I understand the question. Okay, I can explain you
Later.
afterwards. Okay.
Yeah. Yes, please.
So
Later.
let me finish.
Okay.
And it means that when you increase the pH, your near surface layer appears to be with smaller disorder. It means it became again absolutely, and the bigger level it disrupted, something like that.
No, it means simply increasing the thickness, nothing else.
Yeah. No, it is just increasing the thickness of the damaged layer at the surface only.
Okay.
And which is interesting on that slide is that for p ions, bulk damage peak grows up pretty higher.
The mobility.
Yeah. Not it means that p ions can play chemical role preventing the mobility of gallium sublattice defects.
Yes, thanks.
The level of disorder.
Okay, please discuss this later.
And may I ask question?
Yes,
Okay.
please.
Yeah, I'm Prashant Karmakar from India. Yeah, it's a very nice talk, and it's very interesting that you got two peaks. One is for the surface, and another is for the bulk. I very curious that is there any effect of the implanted spaces so that are also creating the interstitial or substitutional defects?
Yes, and I mentioned during my talk that the mass of the implanted species play a role in the damage formation. The heavier ion is, then after some ion mass, we can get fully amorphized surface layer, whereas it is not seen for light ions. And another very important and very interesting thing is seen exactly on that slide, as I have already mentioned. For phosphorus ions, it seems that phosphorus itself plays a role when we reach enough concentration of p ions, then mobility of gallium sublattice defects decreases and the peak grows.
But the presence of the implanted projectiles, yes, also creates the damage or inserts of the defects. So can you distinguish that from the damage?
Yes, p ions are not seen in the RBS spectra here. The reservoir peak for p ions is much should appear in the other range of channels, and it is not seen here. Only for heavy tantalum ions it is seen.
Okay, thank you very much.
Yeah, you're welcome.
Are there more questions from online? No. The other questions? I have one question. Can you show the slide number 8? In this case, you can see that 8, maybe not 8. Yeah, yes, this one. Yeah, you see here that the yield from the oxygen sublattice is much higher than in the case of gallium. But besides, we see in this case one order of magnitude difference in the yield due to the cross-section relations. But did you try to separate the oxygen defects and gallium defects in the different sublattices?
Many thanks for that question, but unfortunately, I have no direct technique to work with the oxygen sublattice. We are looking for that, say, for non-nuclear reaction related technique, but it is not yet done. And it is, of course, of great interest to know if the only gallium related defects are so mobile or oxygen also. Yeah.
Okay. Thank you very much. Thanks to the speaker again for nice presentation. And this is the end of our session.
Сейчас большой кофе-брейк и продолжим. Извиняюсь. Извиняюсь, появился докладчик.
So one of our Chinese colleagues appeared in the Zoom, as far as I understand. Yeah, Professor Du, are you there? No. А что у нас уже кофе-брейк? Это еще полчаса. Окей. So, Professor Du, are you there? Are you online? Please turn on your microphone, please. Вы можете ему дистанционно включить, нет? Напишите. Okay, so with some technical issues, we should try to solve them. In short,
Hello.
Okay, yes, we hear you now.
So it's my turn to give the talk.
Well, so are you ready to present?
I have a little problem with my
Presentation, slides?
earphone.
Earphone, okay. Дайте, пожалуйста, эту бумажку. Спасибо. Okay, so are you ready now? Please show your presentation. Please show your presentation. Can you hear us, Guanhua?
Sorry. Do you see my?
Yeah, but I guess
screen?
that this is not the first slide.
Yes, I think I have some problem with my. But you can hear my voice clearly, yeah?
Okay, you please come to the first slide of your talk. It is, I guess it is not the first, yeah? Okay. So please start.
Yeah. Sorry for the disturbance of my system. So I just changed my title a little bit. But today I will give a talk on single event imaging in microelectronics using single arm microbeams. So which can give you an image of the microelectronic system from millimeter to nanometer scale. So is this okay? The voice, the sound is okay for you? So I think that most of you know
everything is here. So please.
Microelectronics is a severe problem in space applications because of the spatial radiation in outside of the Earth can induce strong defects in microelectronics even by single particle radiation. And normally these kind of chips will be tested on ground, use big accelerators with high energy beams. And with such kind of radiation, you can get the overall cross-section of each chips and can predict the lifetime or the which it can work in normal states on its orbit. But once it has some problem, it has some defect induced by high energy beams, you cannot target where the position of this weak point. So normally you can use such a microbeam to locate the error, or you can even use the microbeam to position the the weak point and to test different radiation hardening techniques. Normally, this can be done with a focusing microbeam system. So with such microbeam system, you have object slates which can first form 100 micrometers size beam, and then this beam was then further focused by a quadruple system, either 4 quadruple magnets or 3 quadruple magnets. With such system, you get the distribution or the location of the single event errors. For example, this shows pioneer work performed at GSI by Bernd Fischer, which she tested the 1 to 0 or 0 to 1 offset in SRAM chips. With such kind of system, you can locate the error and you can establish the connection relationship between the offset and the MOS transistors. And this is the 2 typical imaging methods which used in the last 3 decades. Use either a microbeam system, as I introduced before, and also another system which called secondary particle emission system. And in this system was established in Sandia National Laboratory and in INFN with Padua University in Italy. In this system, they use typically a millimeter beam. Sorry. Use a millimeter beam or sub-millimeter beam, and then transport through a hole of your positioning detector. Afterwards, you detect the secondary electrons or secondary photons from your system, and then decide where the original bombard ion is. And with such method, you can also establish the imaging of the single event occurrence. And one of the main problem of the single event imaging is that you have to use a very high energy beam, which also has enough LHC to simulate the space radiation in the outer space orbits. And also this kind of high energy ions, which has to have a very long range to reach the energy of the space radiations. And today, with the advance of the microelectronics fabrication techniques, the resolution requirement has to be less than 1 micrometers. This is very challenging for a traditional microbeam system. And also because the system, the microelectronic system gets more and more complicated, and even there are some system on chip design. So there are a lot of connections with between chips and with the communications of the peripheral system. Therefore, you need a lot of cables and communication lines to make the test. And in the last decades, the challenge of single event imaging is that the resolution remains at 0.5 microns. This was achieved by GSI almost since 20 years. But the feature size of the chips has reached to 10 nanometer regime. And with a higher beam energy, so for the microbeam system, you get a worse microbeam resolution because the energy is high and you get it's very difficult to focus to get a very clean microbeam system. And also that we need a lot of new techniques to solve the problem with advanced packaging chips. For example, in this is an example of the chip structure of our SRAM system. This is the surface polymer protection layer, which has tens to hundreds of microns, and this can be easily removed. And afterward, there are 10 micrometer thickness before you reach the transistor layer. And therefore, for a normal low energy proton microbeam, you cannot get very high resolution after 10 micrometer thickness. Therefore, we proposed imaging use very high energy beam, and because for such high energy heavy ion beam, it has a very strict ion trajectory. It has less. You can see from here that we have 100 carbon, and you almost see no scattering of the original beam. And we propose to use such high energy ions to imaging the single event effect in microelectronics. And such high energy heavy ions also can simulate, have the similar energy and have the similar penetration depths as the radiation, space radiation in the satellite orbit. For example, this is previous work performed at GSI. Use their microbeam, it can reach here like 1.1 micrometer in X and Y directions. With this direction, we can study the silicon carbide most LTEs, which is used in high voltage power supply systems, and also used in high-speed train system, or also used. This can be used also in electrical vehicles. And for this, we can see very clear the fabrication structure of this silicon carbide. But with this 1 micrometer resolution, you get you can see there are some relations, but because of the bad resolution, you cannot get a very good result. Therefore, we need to get higher resolution to really establish the relationship between the effect and the structure inside the chip. And this is what we do in Lanzhou with our interdisciplinary heavy ion microbeam. This is located in the National Laboratory for Heavy Ion Accelerators, which we located here. This means we can use the first 2 cyclotron with energy of several MeV per nucleon up to 100 MeV per nucleons. This is how our system looks like. This is the horizontal beam line, and then we burn the beam by 2 times 45-degree magnets down to the basement, and then the beam is focused here. And then one form of the cyclotron system gives you a multi-turn extraction, which is a big problem for microbeam imaging. For example, this is one of our bad example. We can see clearly 3 beam spots, actually 3 energy extracted from this cyclotron. But this can be easily removed by insert of energy slits between these 2 45-degree bending magnets. And also we can remove the scattering on the microslits with this bending design, of by the bending magnet fields. This is very important because for such high energy heavy ions, it has very long range in steel. For example, for traditional 7 MeV proton microbeam, for example, like a 2 MeV proton microbeam, it has only 2 MeV proton has only a range in steel like 20 microns. But for 1 GeV carbon ions, it has a 3.5 millimeter range. Therefore, it has a lot of scattered ions. If you do not remove these scattered ions, for example, if you use such a straight microbeam system, these high energy scattered high energy ions will influence your microbeam, will really destroy your microbeam resolution. But with a bending system, this problem can be removed. This is how it looks at our end station. We have a triplet positive magnet, and the beam comes from here down to here, as you see from here, and then the system, the chip is located on a microscope. Here is actually the vacuum window. The microscope can be moved down to the vacuum nozzle, and then we located the chip micro area with this upper microscope, and we can also use locate the chip with microscope in vacuum. This is what we have performed. We have done with our microbeam. We have established a single arm head system, and we have also established a raster scan system. We can write a single arm patterns as what we want. The interdisciplinary application of our heavy ion microbeam focused on single event effect, unpacked nanofabrication, and biophysical studies. But today I'm focused on single event imaging. This is how this imaging system looks like. So with the focused microbeam, we connected the beam position by computer control. You get the beam position of X and Y, and then you can switch off the beam by within 1 microsecond. And after you irradiate your samples, your chip gives you a offset signal, and you can establish the beam position and the offset signal, and then you get your single event imaging. Sorry, these are Chinese, and these are some applications we have tested of one chip which has been used in our damper satellite, which has been launched by Chinese Academy of Sciences for search of the dark matters. And this is the single bit offset imaging of one of these chips. And we have done a lot of different systems like SRAM, like silicon carbide diode, like ferroelectric SRAM, and digital processors. We can also use this microbeam to large area single event effect mapping. And you see, this is almost 1 centimeter square chips. We can do this scanning over the whole chips, not only by scan the beam, but also by moving the sample stage automatically, and then establish this single event mapping. And this single event mapping can be done by multi-channel simultaneously. We have done this multi-bit offset with 1 to 0 and 0 to 1, and also latch up event this 4 channels together. At the same time, we also, with our collaborator, we use our microbeam as a fault injection tools to attack some secured chips, encrypted chips. And so the principle of this application is to induce the upset of the system when it's doing encryption or decipheration. And with this induce of this upset, it can induce a leakage of the password. And because the resolution, as I showed you before, is much worse than 1 micrometer or than sub micrometer. Therefore, we established a high resolution single event detect microscope. This is our invention, and with this method, we use single unlocalization and establish the correlation between the ion position and the ion effect. This is how it looks like. We use a 250 micrometer beam spot. There's just a weak focus of our microbeam system, and then we started the ion beam induced charge collection in a pixel detector, which is this pixel detector is used for nuclear physics studies, which is a top metal pixel detector made by Professor Xiangming Sun at Huazhong Normal University. As you see here, this is 1 pixel of this detector. And normally you get only one signal from the whole chip, the whole pixel. But with our imaging method, actually you know where is the signal come from, where the chip is not sensitive to the radiation at all. For example, like this area, if the ion hit here, the chip detector gives you no signal at all. Only these areas are sensitive to the ion radiations. And this method demonstrates, this image demonstrates that it's very easy to get sub-micron resolution of this single event imaging with our new techniques. And this is a single event upset. So this means from 1 to 0 or from 0 to 1 upset using our new method. This S-RAM is made, has a feature size of 350 nanometers. Each bit has it's about 4 times 4 micrometer squares. And we can clearly see the single bit offset here, and we also want to know inside each bit offset the location, how its correlation, the correlation with the most transistors. This is the cut of the same chip done with FIB. This is the SEM image of the same chip as we performed with our single event imaging microscope. And we after the simulation we found that this is the Q. The blue means 1 to 0. This is where the data is stored as 0. This is the sensitive area where the data. The red is the sensitive area where the data is stored as 1 in this bit, and the blue is where the sensitive area where the data is sensitive is stored as 0. And this is how it looks. It's in reality by our imaging method. You see that this is 1 bit, and each bit is here. We get it like 3.5 times 4. Yeah, 3.5 times 4 microns. This is the 1 bit and we can revolve with our high resolution method. We can revolve the single event offset, the offset subregions. This is the area where it's 1 to 0 sensitive areas. This and the two corners, and the middle part is when the data is stored as 0 to 0. This means it's 0 to 1 offset. This means 1 to 0 offset. Also, it's very similar, and also found there as a mirror structure in these chips. Furthermore, we use our microbeam system. We also establish a bitmap decryption model. This means with our system, we can decipher each bit, where the location of each bit on the SRAM. So this means if I give you a paper, so I can actually change each letters in this paper because you know the position. This is the thing, and this is most of this work was performed by Jinlong Guo and Guangbo Mao. These are my two graduate students who doctoral students, and with this I thank you for attention. Sorry, because of the voice, I cannot hear clearly.
Thank you very much for a very nice talk. And now it is open for discussion.
If you have questions,
can you hear us?
Type on the. Sorry, you can type on the screen.
Can you hear us, Guanghua? So can you hear us?
Yeah, I can hear
okay,
you.
Okay.
But because
any questions, please?
I just changed my system, changed my computer. I have new office, so I'm not familiar with the.
Okay. So we have questions here in the audience, and please, yes.
Thank you for the interesting talk. And the question is about, can your technique be applied to the resurrection of the deleted information?
Sorry, I did not hear clearly. Could you could anybody can type it on the chat?
Sorry, we have a very poor connection. So the question is, can you use your system to delete information?
Sorry, I'm sorry. Oh, sorry. Can anybody type?
Let me to repeat the question. It is about.
I have a new computer. I don't know. I did not install my. Yeah.
Okay.
So,
Ivan, еще раз.
Okay. The question is about, can your technique be used to restore the deleted information from the RAM at other devices?
Can you restore information? Can you restore information?
So I can. Sorry, I'm really sorry. But anybody can type can help me to type this question, and I will answer in the chat. And I will not. Maybe you can continue with the next talk.
Да. Okay, we can type quick questions if you have some more.
Can I restore? Can you restore information? Restore information. Can I restore information from what?
Yeah. Okay. I can. I guess he can't. Your question.
I just did not understand the question. I can.
Thank you for your presentation. Can you hear? Just
I
ask
can
and
hear
we will
you.
type. Yeah. Okay. So probably I missed, but does your technique destroys the chip? So it's.
Could you speak louder?
Does your technique destroys the sample, the chip?
No. Yeah, you're right. We destroy the sample from time to time because the imaging method actually delivers very high dose of heavy ions. So this is normal. But you can, if you use lighter ions, maybe the imaging, you can get a better imaging, how to say that, you can get a better imaging, but it's true that you may destroy the chips. So you have to balance, because sometimes you need very high LTs, and also you need a very high resolution. So you have to, with high resolution means you have to hit at very small step to your chip. I hope you understand me.
Partly. Thank you very much. I guess. Yeah. Okay.
So we sometimes we have to change the. We detect the signal from the chip. So if you have an analog chip like FET, you want to detect the leakage. You want to detect the burnout, for example, or overcurrent. So you can use the analog signal from a chip to correlate with the beam position, to correlate with the ion position, X or Y. And for the digital system, like the SRAM, which stores the data as 1 or 0, so you have a system which to check your SRAM very fast. So once you detect the upset, so you establish the correlation between the beam position and the effect. The total charge of secondary electrons. That is a good question for the single event study. So actually, normally I will show you this one. I will share the screen. Yeah, and for this, is for a single event study in microelectronics. So the charge comes from the radiation, the interaction of the ions with the semiconductors, and also come from the stored or trapped charge in the PN junctions, in the PNP junctions. So there are several ways to describe the charge collection, but this charge collection, either it comes from direct radiation or comes from the stored charge. Both of them can induce the defect, induce an upset, induce overcurrent, induce a burnout. in microelectronics. And here I think the secondary electrons, it's of course.
Well. Thank you very much for your explanations. Thank you very much for your explanations. But I think that we are now running out of time. And thank you very much for a very nice presentation. Let's thank the speaker again.
I cannot visit Russia.
Thank you very much.
I hope I will be there next time.
And as we somehow delayed with the end of this session, we will ask our chair to postpone the start of the next.
Так, ну, кофе-брейк.
Yes, good afternoon. We start our next. We continue our morning session, and the first talk for this session is Давид Исакович Тетельбаум. Электрофизические свойства монокристаллов бета-галлий-2О3 железа с ионно-легированным кремнием. Давид Исакович только что был здесь. Так он только что был здесь. Ага, вот все. Давид Исакович, как вы? Давайте. Я вам включу.
This is the name of my report. I should not speak very much about this material, oxide, gallium oxide, because it is shown by Dr. Gogol and Karasев about importance of this material. I only could to speak about the very high publicity for this material. It is because this material is very important for modern electronics, and the quantity of the article, annual article, is about 1,000. It is very much for one material. And what is about the ion implantation for oxide gallium? It is in initial stage because the main application what for the such areas as so for ohmic contacts, for channel field effect transistor, and partly, and this is for US element modification, but it is very limited employment, and more wider employment is not possible without the physical-chemical investigation of this process. But this area of research is in very, very initial state. Our aim is to partly to fill these gaps, and we implanted the silicon ions into the materials, into the ion oxide gallium. Why we select this material? Because this material is widely employed for as substrate for for epitaxy, but direct implantation into this material should exclude not so expensive methods as epitaxy, and more fully use the preference of ion implantation. It is known that this is the main methods in modern microelectronics, but for this material, as I said, it is initial stage of investigation. The methods of implantation is shown. The silicon ion was about 100 keV, and other parameter is shown on this slide. The annealing was in the tube furnace. Atomic contacts for whole investigation was by usual methods. This picture shows the change of structure of oxide gallium after ion implantation and after the annealing. It is seen that after implantation, the layer with strain appears, and this strain is this strain is under subsequent annealing diminished, but some residual defects retains for 1900 centigrades. It is the comparison of with initial sample. And this is high resolution X-ray diffraction pictures for different fluences. It is seen that complicated picture, complicated dependence for the doses. Each dose is characterized by its own picture, as is seen for initial and for different doses cases. This is the results of secondary ion mass spectroscopy. It is shown that the depth profiles is not changed up to up to 19 centigrades of annealings. And more interesting result was achieved for electrical properties of implanted layer. this is the table, and this is the results. What you can see, we see that after high annealing temperature, the effectiveness of doping is anomalous high, and coefficient of doping efficiency became more than unity. This is not usual for the ion implantation, and moreover, for oxide gallium, nobody have seen this effect. What is the cause? Evidently, not only silicon, but other shallow defects can get impact for the electrical properties of these materials. What is these defects? Evidently, our distinction is the distinction of our material from the other investigation is that it contains the iron, and we can speculate this, namely the iron or silicon are responsible for this anomalous effect. In order to more clear to know what is the cause of this effect, we have taken the temperature of electrical properties from temperature dependence. And what we see, the concentration of silicon of electrons is nearly constant, not depends on temperature, on temperature sample. And mobility is some dependence, have some dependence. The constant character of the carriers of the electron concentration, it is this is usual effect, and this is shown that this material is heavily doped, and it is in danger, the degenerated state. But why is this the behavior of the mobility? For the generated semiconductors, we should expect that mobility also be constant, but we see that it is not fact. For the explanation of this phenomenon, we use some model, and we can see this model is on the right picture. this model is characterized by two additional levels in the deep levels. One of this level is deep donor, and another is the acceptor. And these levels are caused evidently by defects, some defects. What is this defects? We don't know now, but theoretical, but fitting experimental data with theoretical calculation shows that this model can be used for explanation. This is electrical dates for other doses, for other fluencies. It is seen that behavior is also not usual, that no, but this dependence now is very difficult to explain. It is required more investigation in order to understand. And this is a conclusion. The electrical properties of the layers obtained by ion implantation of silicon in semi-isolated oxygen, gallium oxygen doped by iron were studied for the least time. So the deepening effect, as I say, was found, which means that the efficiency, the coefficient of activity efficiency annealed at high temperature significantly exceed the unity. And the dependence of electron mobility of temperature for sample with this effect suggests the presence of donor and acceptor centers additional to silicon. Such centers we propose that they caused by defects in the formation, some defects in our sample, and the formation of this defects complexes is involved the silicon atom and iron. Thank you for the attention.
Thank you very much for a very interesting talk. And on behalf of all our colleagues, I would like to thank our mastodont in ion implantation with his jubileum. And it is my pleasure to present your answer on the questions. This report is open for discussion or for the questions, please. Okay.
Is it, from your opinion, possible to get P-type gallium nitride by implantation? Do you know any paper in this field?
Silicon for gallium nitride. Please in microphone. I'm sorry.
This is more interesting problem, and наши исследования будущее как раз должны быть направлены на то, возможно ли получение все-таки P-типа. Это очень трудная задача, потому что до сих пор, как вы знаете, P-тип получают, если получают, то с очень низкой концентрацией дырок, а для практики требуется, конечно, высокая концентрация. Вот. Ну, есть несколько работ теоретических, не наших работ, где предлагаются некоторые методы, каким образом можно попытаться получить P-тип. Вот. Ну и наша задача в дальнейших исследованиях стоит в том, чтобы экспериментально проверить. Ведь это действительно очень важная проблема. При имплантации вводятся комплексы, часть из которых может, в принципе, находиться, их уровни могут находиться близко к валентной зоне. Вот. И если это так, то тогда действительно можно получить, в принципе, P-тип. Но, конечно, эта задача очень непростая.
Еще вопрос? More questions? Давид Сакович, may I ask you? Какое-то есть предположение о концентрации вырожденного центра, донор-акцептор, и его энергетического положения в этом материале? То есть, поскольку температуры очень низкие, при которых вы нагреваете, это всего там 300-350 градусов Кельвина, по-моему, да, было?
Нет,
подвижности.
Нет,
Цельсия?
мы нагреваем до 950 градусов.
Ага. Хорошо, да. Но вот все-таки уровень этого дефекта.
Поскольку в литературе имеется сообщение о том, что даже при таких высоких температурах отжига дефекты все-таки сохраняются, ну и действительно мы видим и по рентгеновским данным, то можно предположить, что вот эти уровни глубокие, а то, что они глубокие, в этом особого сомнения нет, потому что дефекты, как правило, как раз носят глубокие уровни. Вот. Мы долго возились с этой проблемой, ну и удалось в конце концов подобрать такую модель, которая довольно неплохо описывает эту зависимость подвижности от температуры.
Но это акцепторный уровень, который вблизи зоны проводимости, ведь тут далеко до собственной проводимости.
Нет, это не касается проблемы перехода в P-тип. Это касается проблемы легирования кремнием, а кремний дает N-тип.
Это понятно, да.
May I?
Okay, one question more.
David Isakovich, have you measured damage formed and its evolution under your annealing?
The evolution of the peak.
That damage.
Абсолютное значение стресса. Или относительное.
Evolution.
Да, вот здесь примерно.
Видно, что после небольшого отжига идет восстановление. Значит, само по себе облучение вызывает эту область, где осциллирует интенсивность рентгеновского излучения дифрагированного. Эта область, она показывает, что имеется, что имплантированный слой испытывает латеральное сжатие. Ну и, следовательно, расширение в перпендикулярном направлении. Вот. А после отжига происходит существенное восстановление. Однако, как видно, вплоть до самых высоких температур, пик остается шире, чем исходные слева, и поэтому остаточные дефекты сохраняются.
Это для того же образца, что вы мерили про проводимость и подвижность? Или это для другого образца?
Нет,
Вот.
это для того же самого образца. Это для того же самого образца.
Yeah, okay. Thanks.
More questions? Then please speak. Thanks to the speaker again. Our next presentation for this session. Смирнова, Лобзов, Лебедев, Маталинский, Пухов, Васильев, Бачурин, Чурилов. Волнообразные периодические структуры на поверхности кремния, инициируемые облучением фокусированным ионным пучком галлия. Пожалуйста, 15 минут.
Good afternoon, dear colleagues. My name is Maria Smirnova, and I would like to introduce to you, thank you. And I would like to introduce to you the work of Yaroslavl team, which name is Wave-like periodic structures on the silicon surface initiated by irradiation with a focused gallium ion beam. Recently, the formation of nanometer scale periodic structures, including the wave-like periodic structures on the surfaces of various materials, such as metals, semiconductors, and dielectrics, has attracted a great interest. A comprehensive review of experimental and theoretical works devoted to the formation of wave-like relief on solid surfaces under ion beam radiation can be found in the work cited on the slide below. Figure 1 shows possible variants of the morphologies which can form on the silicon surface irradiated with gallium ions. The formation of wave-like relief occurs under certain influences with depends on the type of ions. On the slide are given the orders of magnitude of such influences and energy ranges corresponding to the ripple nucleation under irradiation with noble gases, oxygen and nitrogen respectively. The wave-like relief formation is observed in a certain range of ion beam incidence angles, and it was experimentally established that for noble gas ions, this range is from 45 to 60 degrees, and for chemically active ions, this range is from 30 to 60 degrees. Within the framework of the linear continuous model of surface morphology development described in detail in the work cited on the slide below, equation number 1 characterizes the time evolution of perturbations H of a flat surface due to ion radiation, where U and V are coordinates coinciding to the ion beam direction and perpendicular to it, respectively. Here, you should see below. Here, the angle-dependent curvature coefficients SU and SV, and B coefficient in equation number 1 is the coefficient describing surface diffusion with surface diffusivity ds. The first summands in the curvature coefficients equations are related to the angular dependence of sputtering. This is Bradley Harper mechanism. And the second summands are related to the mass redistribution in the collision cascade volume. This is Carter and Vishnikov mechanism. Wave-like relief occurs at incidence angles when one or both of the curvature coefficients have a negative value. At the bottom of the slide, the conditions for the emergence of wave-like relief with a parallel and perpendicular wave vector to the direction of the ion beam incidence are shown respectively. Earlier in the works cited on the slide below, it was shown that under irradiation of silicon with 30 kiloelectron volts gallium ion beam, a perpendicular wave-like relief to the ion beam direction is formed on the surface in a narrow angular range near 30 degrees. Relief nucleation starts with fluences 2 multiplied by 10 power of 17 ion divided by centimeter power of 2. And figure 2 shows the case of steady state wave-like relief. Also, previously, it was experimentally determined that at ion beam incidence angles exceeding 40 degrees, the surface remains smooth. At fluences more than 10 power of 18, as you can see in figure 3. In this work, the curvature coefficients were calculated for the case of irradiation of silicon with 30 kiloelectron volts gallium ions under the model proposed by Hans Hofses. The results of calculations you can see in figure 4. The figure shows that at incidence angles from 30 to 70 degrees, transverse wave-like periodic structures can be formed on the surface, and at incidence angles from 75 to 85 degrees, longitudinal wave-like relief is possible. As noted above, transverse wave-like relief on the silicon surface under gallium irradiation was observed only at incidence beams near 30 degrees. Implanted gallium ions in the near surface layer do not form chemical compounds with silicon atoms. In the work of Frey et al., it was shown that gallium ions implanted at normal incidence are present near the surface as precipitates of few nanometer in size. There is that gallium ions is inert with respect to the silicon. Then it can be expected that appearance of wave-like relief on the silicon surface and gallium irradiation at angle exceeding 30 degrees will occur at fluences close to 10 power of 19 ion divided by centimeter power of 2, as in the case of bombardment of silicon with noble gases. Experiments of silicon sputtering with 30 kiloelectron volts gallium ions were carried out on a Quanta facility. The main experimental parameters you can see in the left side of this slide, and further detailed study was carried out on Supra facility. This is scanning electron microscope. As a result of this research, it was found that periodic structures appear on the silicon surface under incidence angles exceeding 40 degrees, but fluences are an order of magnitude higher than the case of irradiation at an 30 degrees incidence angle. Figure 7 shows the case of irradiation at incidence angle equals 40 degrees. The ripple nucleation starts at the edge of the raster surface, and with fluence increasing, a periodic structure covers the whole surface of the raster bottom. As you can see in figure 8, incidence angle equals 60 degrees. Here we can see two cases of irradiation at incidence angle 30 and 50 degrees respectively. We can see that in the first case, letters A and B A periodic wave-like relief with wavelengths of 150 nanometers is formed, and in the second case, let us see, a periodic structure in a terraced form with a period 1.5 micrometer is formed. Here it can be seen that the side of the structure facing to the ion beam is rouge, and the opposite side is smooth. In the work of Rudy et al., it was shown that the appearance of periodic structures produced by ion beam radiation can change from sinusoidal to terraced with fluence increasing. Possible reason of the difference in the values of fluences corresponding to the ripple nucleation at different ion beam incidence angles is the presence of gallium precipitates in the near surface layer. In accordance with the linear theory of ripple nucleation, the necessary condition for the appearance is the instability of surface topography. This instability arises due to different sputtering rates of chemical compounds precipitates or gallium precipitates. There are, you can see some images of silicon surface irradiated with gallium and xenon ion beams at the same fluence on the slide. It can be seen that in the case of bombardment with noble gases, there are no ripple on the surface. There are no ripples on the surface at given fluence. The topographic in the other case has surface instability, and this is due to accumulation of defects in the near surface layer. Figure 10 shows the same image of the silicon sample cross-section after gallium radiation, angle of incidence 30 degrees, and fluence equals 10 power of 17 ion divided by centimeter power of 2. It can be seen that gallium precipitates of 510 nanometer in size are present in the near surface layer, and the sputtering rate of these precipitates is almost 2 times faster than the sputtering rates of initial silicon. This leads to the topographic surface instability and appearance of ripples, and at noticeable surface erosion, that is fluences exceeding 2 multiplied by 10 power of 17. Previously, we obtained angular dependencies of silicon sputtering yield and gallium concentration in the near surface layer and irradiation with focused gallium ion beam. Figure 12 shows that at incidence angles exceeding 30 degrees, there is rather sharp decrease in a gallium concentration. Recall that the gallium is inert with respect to the silicon, and therefore the appearance of topographic instability apparently is associated with the accumulation of defects, which requires high doses of radiation. And we came to the conclusions. You can read them on the slide. Thank you for your attention, and I would like to answer your questions.
Thank you very much for a very nice presentation. Please, your questions.
Спасибо. Можно слайд 13? Вот вы не пробовали получать последовательно, то есть после небольшой дозы галлия ксеноном? Интересно, будут ли преципитаты галлия служить зародышами для ксенона? Кнопочка есть.
Спасибо. Честно, нет, мы не пробовали. Дело в том, что данные образцы изготавливали на разных установках. У нас чисто физически, к сожалению, пока нет возможности сделать это последовательно друг за другом. А преципитаты галлия, насколько нам известно, они особо долго не живут.
Спасибо. Please, more questions. Давид Исакович.
Причина отличия такого сильного облучения галлием и ксеноном? Вроде бы не должно быть сильного отличия. И тот, и другой.
То есть вы имеете в виду, почему в одном случае у нас появляется какая-то морфология, в другом случае нет?
Нет, у вас вот разные картинки слева и справа. Почему такое отличие? Слева есть ripples, а справа вот не видно.
Все дело в том, что в случае кремния мы набираем достаточную дозу для формирования преципитатов при поверхностной области, а в случае облучения с ксеноном эти преципитаты не образуются, и поверхность у нас остается гладкой. То есть наличие какого-то исходного рельефа, которое может быть вызвано накоплением дефектов при дальнейшем распылении, оно является необходимым условием для возникновения риплов. То есть в том случае, когда преципитатов нет, и риплов тоже нет.
Спасибо.
Please, more question. Not? Maria, I have a question. Did you measure the surface conductivity of your film in the case of the formation precipitate or not?
No.
No? Because it is very interesting question for diamond, for carbon. It is well known that these chemical not active atoms create some kind of superconductivity.
Thank you. I think that we will do it in the future.
Okay. One question more.
А скажите, пожалуйста, вот зачем вам было получать эти галлиевые преципитаты?
Дело в том, что мы не то чтобы намеренно их получали. Галлиевые преципитаты – это еще одно подтверждение теории, которая была выдвинута. Вот, то есть, если вы посмотрите внимательно на уравнение номер 2, то в этом уравнении последнее слагаемое, оно как раз отвечает за исходный рельеф. И, как я уже говорила, что вот эти преципитаты галлия могут рассматриваться как исходная неоднородность распыляемой поверхности, и за счет как раз различия скоростей распыления галлиевых преципитатов и исходного кремния у нас возникает это нестабильность поверхности, то есть риплы. То есть риплы, грубо говоря, это не цель, это следствие. Мы хотели объяснить, почему и как у нас формируется этот волнообразный рельеф, и это как раз является одним из подтверждений теории.
Вы объяснили, почему он появляется? Вопрос, и как он появляется? Потому что, судя по всему, если уж получать это, вы, наверное, хотите гладкую поверхность получить, да? А если получилось вот такие холмы, то тогда объяснить, почему они получились и как сделать, чтобы они не получались.
На самом деле мы исследуем как раз не гладкую поверхность, и цель была именно в получении периодической волнообразной структуры. Еще раз повторюсь, то есть как это происходит. Мы начинаем облучать поверхность кремния ионами галлия, доходим до определенной дозы. В приповерхностном слое у нас формируются галлиевые преципитаты. То есть на рисунке 5 черными кружочками изображены галлиевые как раз преципитаты. После того, как мы доходим до слоя с преципитатами, у нас появляются области, содержащие галлиевые преципитаты и не содержащие их. Таким образом, по мере распыления поверхности в целом у нас появляется разность в скоростях распыления этих преципитатов.
Понятно, извините, а почему получается, где-то есть преципитат, а где-то нет?
Потому что где-то быстрее распылилась поверхность, где-то медленнее
почему?
она распыляется. Разные скорости распыления у разных материалов.
Тогда должно быть в одном случае гладко так, а в другом случае как-то по-другому. Почему на поверхности появляются...
Потому что преципитаты располагаются у нас не сплошным слоем, а с некоторыми расстояниями. То есть они сами по себе имеют форму шариков таких, скажем так.
Шариков.
Так они скапливаются. Это уже не по нашей теме немножко.
Я хочу сказать, что это очень интересное вообще направление исследования.
Здесь на самом деле вопросов остается достаточно много, потому что область исследования достаточно интересная, и есть еще о чем подумать. То есть мы сделали на данный момент какую-то часть исследования.
Сосредоточиться на чем-нибудь. И вот в этой области на чем-нибудь. Одно дело там аргоновые ионы, другое дело какие-то ионы химически активные, потом галлий, совершенно третье. Эти полосы появились, то это появилось. Ну, хоть что-нибудь вы бы объяснили, да, сами себе.
У нас была работа, на самом деле, достаточно экспериментальная, потому что мы исследовали именно зависимость получаемого рельефа от экспериментальных параметров. То есть мы меняли различные параметры облучения и смотрели, что будет при этом происходить.
Ну, а потом объяснить, почему при таком режиме...
Это уже тема следующего доклада.
Спасибо.
Спасибо большое за вопрос.
Чтобы был у вас следующий этап.
Хорошо.
Очень интересно.
Хорошо.
Спасибо за замечание. Other questions online? No? Today is one question more.
Секунду. Просто это не вопрос, это маленький комментарий к предыдущему вопросу. То есть галлий и кремний с точки зрения термодинамики – это не смешиваемые элементы. То есть даже если вы будете кристаллизовать из расплава, у вас получится просто зарождение отдельно галлия, отдельно кремния. То есть здесь совершенно аналогичная ситуация, твердофазная диффузия, что вот причина появления вот этих вот...
Нет такого соединения карбид галлия. And last questions.
Раз. По 13-му снова вопрос, комментарий. Я, может, пропустил. На разные углы исследовались, просто это как бы и вопрос и комментарий. Я работал с разными материалами, и тоже под углом и разными газами, и, возможно, риплы формируются при других углах, потому что на одних и тех же образцах разные газы могут начинать формирование волновых структур под или от 60, только на ксеноне, возможно, тоже формируются. Были ли разные углы для ксенона?
Я с вами полностью согласна. Мы смотрели и при других углах, но цель этого слайда показать, что при одних и тех же условиях на одной и той же поверхности, но различными пучками мы получаем разные морфологии. То есть это как раз подтверждение тех слов, что я говорила ранее.
Спасибо.
Спасибо.
Thank you very much for your report. Thanks to the speaker again, and thanks to all our speakers at this session. And announcement from organizing committee.
К сожалению, у нас сегодня получилась короткая сессия. Значит, обед по расписанию в 13:30, и у вас есть время немножко погулять по городу, пока не пришел еще дождь. В районе профинтерна дождь уже начался. Значит, члены оргкомитета, программного комитета, значит, остаются, а все свободны.
Время уже 13:15. 15 минут.
Ой, извините. Как 13:15? Я не посмотрел. Я извиняюсь, мне почему-то сказалось 12:15. Все, тогда на обед.
Да, практически нет. Если что, можете побольше. Все было максимально приближено к реальности. Можешь дать, пожалуйста? Там, помните, вот был там, а меня уже не будет. Я думаю, вы просто не так дайте. Я вот возможно такая проблема. Вы когда начинаете демонстрации экрана, какой экран? Ага, ну я понял, дублирующий экран. То есть вы, а если экран будет? Нет, там по организации просили, что ладно. Ребят, можете, пожалуйста, как вчера сделать и демонстрацию экрана? Ну да, чтобы 1,5 часа. Пустой зал. А где кончилочка ставки? Да, у меня там зеленая. Зеленая составка. Ну, как вот это, который будет. Программа. Кто-то из вас там, наверное, как-то должна быть. Наверное, Если что, я вот вчера понимаете, Ты кого-то знаешь? Вот. Короче, один может всегда оставаться здесь. Возле в зале даже не будет, парциально должен а потом вроде бы есть, можешь выходить. А, нет, ты не можешь. Ты даже сейчас тебе парень заставил с флешбеком. Подожди, ладно. Я пошел. Если что, пошел. А на руках я знаю, что я буду смотреть, какая перепись. Если что, мы с вами
Hi. Are you there? Hello. Ó, várjál, lehet, hogy ezt kell, hogy engedélyeztem a kamerát. Csak zsengítre szükséges. Vagy itt van a kamera?
Hát nézd, ott van a kamera, igen, de egyébként itt is van egy másik.
És akkor én itt látszom, most nem látszom.
Most bemutatjuk a kamerát, csak levontak, csak így.
Hogy?
Van egy ilyen kis csúszta.
Aha. Aha, és akkor most ott vagyok. Szuper. Akkor most le lehet venni.
Én mindig, mikor így telepítem, akkor igazából lezárom a kamerát, hogy ne... Tudom, mindenki fasik állandóan, hogy úristen, biztos valaki meg fogja figyelni a kameráján keresztül.
Nem is tudtam, hogy itt van. Én le van hajtva nekem ez, tehát oda be van csúsztatva alá, de most ezen akarom tartani, hogy mert volt egy-két online előadás, és nagyon szakadott volt. És féle. Tudod, párszor már tartottam ezen, és nem volt jó. Most ez akkor rendesen megy. Jó, ezt letettem. Akkor ez működik most? Működik, mert ott működik csak. Szuper.
Ennek a kamerája szerintem nagyobb felbontású. De mondjuk ebből nem vagyok 100%.
Akkor meg tegyük vissza, mert így nagyon látszik a szobám. Mekkora kupleráj van itt.
Erre, hogy ez ott van a virágon.
Jó, ez. Keresek papírok. Jó, és akkor, jó, hát remélem működik. Most nincs még bent senki.
Вот так вот рабочий зеленый, а будет гореть красный. То есть некоторое время еще он поработает с красным. Но нужно как бы
Hello.
Hello, we are on pause for coffee break.
I know I am Karo Tökési from Hungary and I will be the second speaker. So if you are there, can you help me to check if my presentation is correct?
No problem.
Oh, thanks.
You can show and we will say you the feedback.
Okay, so what I have to do is just share the screen. Is it correct?
Of course. And before you do it, you need to open your presentation.
Yes, I open it. And just quickly, I would like to, I have a few online presentation and none of them was perfect. So I know I would like some perfect presentation, okay? So just I share and what I have to do. PowerPoint. Okay.
No problem.
I know. Do you see it?
Yes, we see.
And no, I have to go presentation from the beginning. And it's working?
Fine, we saw it perfectly clear.
Okay, but how can I do that? I saw myself here in a window. Megosztás. No, egy másik.
Repeat, please, what you said.
So it seems to be working. Just a second, just I go to the end.
Seems all fine.
Conclusion and okay. See you next year.
Okay.
So now I finish it. And it was good. Hello.
What did you said? I cannot run for you. Can you talk a bit slower? I'm
okay.
not committed.
No, it seems to be everything is fine. Is
Yes.
Both the voice and the presentation.
Of course.
No, I finished and I withdraw the share screen. So apart from this, but what I saw on my screen, I saw only my presentation. Is it okay?
What do you want to see more?
Oh, no, because in a previous time I saw also my face or something like that. So maybe I will not use a video. Maybe I can use just a video right now. But during my presentation, I will not use the video. Is it okay?
You don't see your face because your camera was off when you're showing.
Okay, then can I try to share one more time? Okay, just try.
No problem.
Okay, and what I have to do is up over presentation. Okay, and that's all. True and okay.
In a conference hall, we see you and your face.
Oh, you saw, but I saw only my presentation. But don't mind. If it is perfect, then I close it. Thank you very much for your help. Thanks.
No problem. Good luck on your.
Okay, thanks. Bye.
Is defect engineering in wide bandgap semiconductors. Katarina, are you online?
Yes,
Do you hear me? Oh, okay. Hello. Okay, please.
Okay, thank you. I did not hear the introduction because you were muted for some time. Okay.
Okay, please demonstrate your screen and you may start.
Okay, thank you very much for the introduction, and thank you very much to the organizers for inviting me to give this talk at this nice conference on defect engineering in wide bandgap semiconductors. In fact, I will talk about wide bandgap oxide semiconductors. I just plotted here a few of them. We have really a lot of different wide bandgap metal oxides with different band gaps, and we can choose the material according to the applications that we would like to develop, which range from transparent electronics to displays, batteries, thin film transistors, flexible electronics to power electronics. And for today, I would like to pick out two cases that I would like to discuss and how we can do defect engineering of these materials to enhance their properties. One of the material is molybdenum oxide, which crystallizes in this orthorhombic phase. It is a true 2D material, so it is very easy to exfoliate very thin membranes, just like graphene. And what was interesting to us is that it's possible to tune the electrical properties via the oxygen stoichiometry. So in fact, stoichiometric molybdenum 3 oxide is quite insulating, but as we are creating oxygen vacancies, the material becomes to have semiconducting properties and even metallic conduction-like properties. So our goal will be to irradiate this material with ions and increase the conductivity of the material. And the second case I would like to discuss is defect engineering in gallium oxide. We have already heard several talks today about gallium oxide, so I don't need to introduce much about the material. Among the transparent conductive oxides, it's the one with the highest band gap. So it's possible to tune the n-type conductivity while keeping the good transparency. As we have heard, it has a very high breakdown electric field, which makes it interesting for power electronics. But I want to stress more the possibilities for applications in optoelectronics due to the transparency. It's studied a lot for sunblind ultraviolet sensors, but the transparency is also very interesting for the incorporation of optically active ions, such as rare earth ions and transition metals. You can see here on this graph that it's really possible to tune emission properties from the infrared through the entire visible range to the ultraviolet by doping with different optically active ions. And this makes the material interesting for light emitters, waveguides, phosphorus, and optical sensors. Actually, in 2017, I believe, I talked at this conference about our results on rare earth implantation in gallium oxide. Today, I want to focus on the chromium emission. So this is a typical chromium emission at room temperature. You see here the splitting due to the crystal field and spin orbit, the splitting of the levels, which give rise to this typical spectrum, which consists of the narrow R lines superimposed to a broad band, which ranges from the red to the deep infrared. And I also want to mention this broad ultraviolet blue band, which is typical for undoped gallium oxide. The UV band is normally associated to transitions from the conduction band to a self-trapped hole, and the blue emission is usually attributed to donor-acceptor transition in native defects in the material. So we are interested how the optical properties change as we are irradiating with ions. And we do this in the IST microprobe. You see here a photograph. It is connected to the 2.5 megavolt Van de Graaff accelerator. In the schematics, the beam is coming from the right side. It can be focused to 3 to 4 micrometers diameter. It hits the sample, and we can do these experiments simultaneously. Conventional ion beam analysis, like Rutherford backscattering or particle-induced X-ray emission. We can monitor the ion beam-induced luminescence or ionoluminescence, and we can do electrical measurements all simultaneously. And this is an example of an exfoliated membrane of undoped, nominally undoped gallium oxide of these 4 techniques. From the peaks measurements, we can see that even in these nominally undoped materials, we have trace amounts of chromium and iron inside. From the RBS, we can get information about the stoichiometry and membrane thickness. The IV curves you see here have been taken with and without proton irradiation, so they show that we can use this material as an electrical sensor for ionizing irradiation. But today I want to focus on the ionoluminescence, and you can see here the typical blue band as the ion beam is moving up and down on our sample. So if we now dope our sample with chromium, and we do this experiment, so in this case we used 600 keV protons. In the beginning, we see the dominant blue band of the native defects, but as the irradiation is proceeding, you can see that the color of the emission is changing, and the spectrum is changing very strongly because we have the blue band that is being quenched, while the red band, due to the chromium emission, is strongly enhanced. So in fact, the proton irradiation is creating defects which will pin the Fermi level deep inside the conduction band, and this will change and enhance the energy transfer from the host to the chromium ions. In this plot, I'm showing you the integrated chromium peak as a function of the fluence. So in a vast fluence region, we have an almost linear increase with the fluence until we have a saturation of this chromium emission. Then we performed some annealing studies. So after annealing at 800 degrees, we completely recover the luminescence characteristic of the S-grown material. So the red luminescence is completely quenched, and we can restart the measurement, seeing the chromium luminescence starting. And we have done this for several annealing temperatures, showing that after 500 degrees annealing, we don't have a complete recovery, but above 500 degrees, we recover the defects and we can quench the chromium emission. And we think that this is quite interesting for applications in optical dosimetry, and it can be used in situ or also ex situ for radiation sensing. In situ, I just have shown you the ionoluminescence change. But after the irradiation, also the photoluminescence is completely different. So in the pristine sample, we have the blue emission, which is the dominant emission, which is after the proton irradiation completely quenched, and we have the chromium emission, which is arising. And we can also do the same measurements using thermoluminescence. Again, before the irradiation, we don't see any signal from thermoluminescence. After proton irradiation, we clearly see several traps which then at certain temperatures will be depopulated and will excite the chromium emission. And then after an in situ annealing at 600 degrees C, this optical activation of chromium is completely quenched, and the thermoluminescence signal is therefore also quenched. So in the following, we wanted to incorporate the chromium ions by ion implantation to have a good control of the profile and of the amount of chromium that is inside. But actually, after the first implantation, we had a big surprise, and our material turned optically completely different. It was no longer transparent. It looked somehow milky. So we thought we have destroyed our material, but if we looked a bit more careful, we saw that we had the formation of such microtubes on the surface. So all the surface was covered in such gallium oxide microtubes. So to understand what is happening here, I have to tell you that the bulk gallium oxide samples that we start with have a surface orientation, which is a 100 surface orientation. And 100 is an easy cleavage plane of gallium oxide. So although it's not a 2D material, it's very easy to exfoliate, for example, using Scotch tape to exfoliate thin membranes. So what we believe that is happening is that when we are implanting our material, we are creating a strain profile in the implanted region. And as the stress that we are introducing is higher than the bonding strength within the 100 plane, we will start to have an exfoliation of the small membrane. And due to the strain profile, this membrane will roll up and form these nice microtubes. And these microtubes are interesting because now we can actually pick them up and we can transfer them to any substrate that we would like to transfer them. In our case, we transferred them to a silicon wafer. Then we can heat up the material, and at around 500 degrees, we see the unrolling of the membrane. And now we have a nice high quality and implanted, so doped membrane on our new substrate. Here on the right-hand side, you can see a film that is showing this unrolling of the membrane as a function of the temperature. And now at 500 degrees, we have the full unrolling of the membrane. And we believe that we have a high quality, a membrane with a high structural quality inherited from the initial bulk material. And we can control the thickness more or less using or by controlling the energy. At the moment, we can get thicknesses be between 200 and 600 nanometers, and areas, the biggest areas are about 1 millimeter. So at the moment, we are trying to understand better the processes that are leading to this exfoliation in order to optimize the process and hopefully get larger areas. It's interesting to have these membranes because then they can, for example, be transferred on a p-type substrate to make a p-n junction. You remember from previous presentation that at the moment it's not possible to get gallium oxide p-type doped. We can also transfer it to a substrate with higher thermal conductivity. We also heard that this is a problem of gallium oxide, that the thermal conductivity is very low. So to understand the strain profile that we are introducing, we performed X-ray diffraction analysis. For this, we implanted a sample with fluence of 5 × 10⁻13 atoms per square centimeter. This is just before the exfoliation is starting. After the implantation, we see in the 2θ measurements a satellite peak forming at lower angle compared to the main Bragg peak, meaning that we have an expansion of the A lattice parameter. And we believe that this is the strain or stress that is leading to the exfoliation. And then we performed an isochronous annealing study. Already at 250 degrees, we have a strong reduction of strain. At 500 degrees, we have an almost complete recovery, which is in agreement with the unrolling of our membranes at this temperature. And we see a full recovery at 1000 degrees. We can also fit this data using the MROX code. It's a code that is being developed by one of our colleagues, and it allows to extract the strain profiles from the XRD measurements. And we can see that the strain profiles follow quite nicely the defect profiles predicted by SRIM simulation. And after the annealing, we see the reduction of the maximum strain until the full recovery at 1000 degrees centigrade. We also performed annealing measurements using RBS channeling. You see reasonably good crystal quality of the virgin material. After the implantation, we see the expected increase of the backscattering yield due to the damage that we are creating. From these measurements, we can extract the defect profile, relative defect concentration as a function of depth. And again, it follows very well the SRIM vacancy profile. And after annealing already at 250 degrees, we have an almost complete recovery of the crystal lattice. So this was a nice surprise for us, because we have been working a lot on gallium nitride, for example, where even at 1400 degrees centigrade, we still do not manage to recover implantation damage. So these results is good news for ion implantation in gallium oxide, showing that we can get good recovery at reasonably low temperatures. At the moment, we are trying to incorporate our membranes in simple devices and process simple devices to show that they are good for applications, and also better to characterize the membrane and the characteristics of our membranes. So in this case, we tried to process a simple field effect transistor using this structure. So we use gallium oxide as the channel materials. In the photograph, you can see here our membrane. We then just using a shadow mask deposit titanium gold contacts on the two extremities. Those will be the source and the drain contacts. The gallium oxide is on top of a wafer of silicon and silicon dioxide. So the silicon dioxide is our FET dielectrics, and we apply our gate voltage to the P-type silicon substrate. And on the right-hand side, you can see the current, the drain current, as we are switching the gate from plus 10 volts to minus 10 volts, showing that we have a good, reasonably fast switch of our transistor, and also a good reproducibility over many cycles of switching. Exactly the same device can also be used as a UV sensor. So in this case, we don't need the gate contact. We just apply a voltage at the two lateral top contacts. And then we measure the current as we are irradiating with a deuterium lamp, which has mainly a UV spectrum. So as we switch on the lamp, we can clearly see an increase over 2 orders of magnitude of our current. And also when we switch off the lamp, we can see a fast reduction of the photocurrent. We do see some persistent photoconductivity, which is very common in such metal semiconductor devices as we are using here. But this persistent photoconductivity is actually much lower than in similar devices which we have processed using mechanical exfoliation using Scotch tape of the same bulk material. So this suggests that we have few defects at the surface and interface of our membranes. So for the last minutes, I want to move to the second case study, which is ion implantation of molybdenum oxide. We are using these lamellar crystals, and just to remind you, we want to implant ions to create oxygen vacancies, and like this change the conductivity of our material, which from the beginning is very highly resistive. So we implanted oxygen and hydrogen. We chose in a white fluent region, and we chose the energy and the fluence to get more or less the same defect profile for both implantations, as you can see here for the SRIM simulations for oxygen and hydrogen implantation. Then we processed simple devices. Again, you putting lateral electrical contacts and measuring the resistance of these devices. And you can see here how the conductance is increasing with the increase of the fluence, which was here changed to displacement per atoms in order to directly compare oxygen and hydrogen implantation. It's possible to tune the conductivity over 4 orders of magnitudes, both using oxygen and hydrogen implantation. So in the case of oxygen implantation, we do not expect any chemical effects, so we should have pure defect engineering. Unfortunately, we cannot do any RBS channeling on these samples since they are too small and brittle. Nevertheless, we can do X-ray diffraction, and I'm showing you here the results. They are very similar to what I've shown you before for gallium oxide. So in the S-grown material, we just have the expected Bragg peak of the main the main reflection. After implantation, we start to create a satellite peak due to the strained implanted layer. This strain then is increasing with increasing fluence until finally it saturates. On the right-hand side, I show you the results of the fitting of these curves, showing the strain within the region of highest nuclear energy deposition, where we see a strong increase for the low fluences, where we are creating mainly point defects, maybe small clusters in this region, and then we start to saturate, which in this strain saturation is usually attributed to the formation of extended and complex defects and maybe some amorphous regions. And it's exactly in this region that the electrical changes are monotorious. So actually we need the extended defects to create this strong increase of the conductivity. Now, before moving to hydrogen, I just want to show you here the highest values of strain that we could measure in this oxygen implantation. Looking here at the upper graph, it is about 2.5% of strain that we can reach with the oxygen implantation. Now moving to hydrogen, for low fluences, we have a very similar behavior. So we create the satellite peak due to the strained layer. The strain is increasing. It is actually increasing to values much higher than for oxygen implantation, 3.5% instead of 2.5%. And we attribute this to the formation of hydrogen bubbles in this fluence range. And another difference is occurring at the very highest fluence, where you can see here the formation of a very well-defined diffraction peak. And this is due to the formation of a new phase, which is a hydrogen bronze phase. And this is confirmed by TEM analysis, shown here for the highest fluence on the right side. From the TEM, we can clearly see that we have three different layers in our sample. The surface layer 1 is about 300 nanometers thick, so it responds to the actual implanted layer. Looking at higher implantation, we see that it's highly damaged, it's nanocrystalline, and we could confirm with Fresnel contrast the hydrogen bubbles, which correspond to these white contrast dots. Looking at layer 3, this is the pristine molybdenum oxide. Electron diffraction confirms the orthorhombic structure. And this layer 2, it's 1 micrometer thick. It's also single crystalline, as shown by the electron diffraction, and we attribute it to the newly formed bronze phase of molybdenum oxide. Now, in the future, we would like to use these membranes, exfoliated membranes, to make a similar field effect transistor, as I showed you for gallium oxide. This is our first attempt using a molybdenum oxide membrane, which still was not processed by ion beams. So we hope we do see already an effect of the gate in the IV curves, and we hope that using in the future our defect engineering strategies that we can optimize the FET characteristics, and we believe that this may be interesting for biosensor applications. Okay, so in summary, I think I hope I could show you that defects are not always bad. I showed you 3 examples how we can enhance optical, structural, or electrical properties by defect engineering using ion beams. And finally, I would like to thank the collaborators who have contributed to this work, the colleagues from IST, and in particular the first 3 students who have been working mostly on these materials. I thank collaborators at Complutense University of Madrid and Shandong University for the growth of molybdenum oxide and gallium oxide bulk crystals. And the TEM measurement is very fresh, was done last week at Ganil by Mamour Sol and Isabelle Monet. I thank the funding for this work, and I thank you very much for your attention.
Okay, thank you. Any questions?
I have a question.
Okay,
Do
Daniela.
you hear me?
Yeah.
Yes.
Hey, Katerina, I enjoyed your talk very much. How the molybdenum oxide was grown?
This was grown by an evaporation solidification method. So basically, we are just heating up molybdenum metal in a tube furnace in an argon flux, and this evaporates at around 600 degrees centigrade. It's then transported, and this the crystals that are being, so the crystals look like this. They will be crystallizing in a large quantity, but very small crystals in the cooler parts of the tube furnace.
I see. And it's the alpha or beta phase of molybdenum oxide?
This is the alpha phase, the orthorhombic.
Okay. I find your idea to implant oxygen in hydrogen in crystalline molybdenum oxide very interesting, because it is well known that amorphous and polycrystalline tungsten and molybdenum oxide have such chromogenic properties. And their porous structure allows reversible insertion of hydrogen or lithium ions and modulation of transmission.
Yeah, so this we did not explore any of these applications, but the molybdenum oxides, there are articles on photochromic applications, also due to the easy intercalation of ions as electrodes for batteries, for example. So also this hydrogen doped or hydrogen containing phases can be quite interesting, also for catalysis and sensing, because it's more reactive as the pristine molybdenum oxide. So in our case, we really, the objective was to change the conductivity in order to optimize the field effect transistor.
Yeah. Thank you very much.
Thank you for your
question.
I wonder if you've looked at the current collapse in this backgated nanomembrane gallium oxide, because when we did a similar thing with our Korean colleagues, the backgating transistor did work in statics, but the current collapse was simply awful. It was not usable at all.
Okay, so
and the reason is that there are quite a few ion acceptors in the material, and they capture carriers like crazy. So if you are using bulk gallium oxide to do that, it is not a very good idea to go that route.
Okay, and you would see this current collapse at high gate voltages, or when would you?
No. You see it as a hysteresis in current voltage characteristics of your transistor.
Okay.
And then we looked at the transition curves.
So actually, in this, those are the very first measurements that we have. So actually, we have done previous transistors on exfoliated, mechanically exfoliated membranes, and we had huge problems of hysteresis, but we thought that this was due to our contacts, because at the moment, at that time, we did not have optimized contacts. In this,
contacts are a problem, of course, but this is also an issue that you have to look at.
But in this case, so we optimized ohmic contacts. So I don't have the results here. So this is really just last month's results. So we optimized the contacts are ohmic, and we do not have strong hysteresis in the curves in this case.
But when you look at the transition curves in your transistor, the collapse is simply awful.
Mm-hmm. So we are characterizing now these devices. So I will pay attention to this. But like these first measurements on these devices seemed fine to me.
Okay, thank you. Fortunately, we don't have time for questions. Let's thank the speaker again.
Okay, thank you very much.
And the next talk, Takeshi Karli, determination of optical properties of solids from reflection electron Ellinger loss spectroscopy spectra. Takeshi, do you hear me?
Yes, I am here. I try to share the screen. Just a second. So I think I shared the screen. Did you see? Do you see?
Okay, please press F5.
What happened?
Please start the demonstration of the presentation, full screen demonstration.
Yes, I did.
Please return to the previous window.
Yes.
And try to press F5.
No, it seems to be okay.
No. Oh, okay.
Do you see?
Yeah.
Okay.
Okay.
So thank you very much. And first of all, I would like to thank the organizers to invite me to this conference. I really would like to join in person and see Yaroslav and my colleague in Russia, but the recent situation is not as good as it was possible. And also I am apologizing because I am using some special kind of ions. So it is maybe the ion of the positronium. So I will focus on the electron interaction with solids. But maybe the results that I will show you, it is interesting for a wide people, wide interest. So I would like to show some new technique how we can obtain the optical properties of solids. And this is, I think, very important quantity. And we can know everything from materials if we know accurately the optical properties of the material. So in principle, my talk is theoretical talk, but is really in close connection with the experimental data, as we'll show you later. So this is a collaboration work between Hungary and China. So I am working in Hefei University with Professor Ding. We are performing the experimental data in Hungary, and we are doing a calculation commonly in China. But I can offer for you, so during the talk, I will show the motivation, and I will show some results how we can obtain the optical properties, so the photon probing, electron probing, but mostly I will focus on the reflection electron energy loss spectroscopy spectra. I will show you the difficulties, and I will show the new technique, what we can call it reverse Monte Carlo method. And I will show a few results what we obtained during the last years. So why we are interested in to determine the optical constant? Because this is really, we have continuous interest and effort in the determination of optical constants of solids due to their importance in both fundamental research and application. As I mentioned, this is really a fundamental properties of the materials, and if we know accurately the optical constant, we practically can calculate everything what we are interested in for a given material. And this is what we are using. But still many materials still lack of this data. And as I also will show later, the available data in the current database are inaccurate. I will show you why. So methods, what we can use. As I mentioned, there is several methods, but how we can obtain optical properties. So let's probe the sample first with photons, and there are mainly three different kinds of methods. It is the reflection spectroscopy, absorption spectroscopy, and spectroscopic electrometry. In all three investigations, we use photons, and photons passing through or interact with the samples, and from the reflection or backscattering of the photons, we can obtain the optical properties of the materials. Other possibility how we can obtain the optical properties if we use electrons as the particle who try to investigate optical properties. So probing the sample with electrons, we can have two main methods. Again, the transmission mode and the reflection mode. What does it mean, transmission mode? If we have very thin sample, and the sample is here somewhere. If we have very thin sample and we have very high energy electrons, the electrons can pass through the sample and can investigate what is inside the material, and we can obtain the energy loss function, and from the energy loss function we can obtain also the optical properties of the materials. Other way of doing is a reflected electron energy loss spectroscopy. Here just a schematic diagram for spectrometer, which is developed in Hungary. So the sample is here, the electron gun is here, so we irradiate the sample with keV electron range electrons, and after the multi-electronic lens sample, the electron is analyzed, and we detect here the reflected electron energy electrons. From this spectra, we can also obtain the energy loss function, and from the energy loss function, as I mentioned, we can obtain also the optical properties. Using the reflection energy loss spectroscopy, we have plenty of interaction processes, but mainly we will focus on two of them, is elastic and inelastic collision, and I will show you how we can calculate these processes later. And why we use reals? So let's compare the technique what we can use for obtaining the optical properties. At first, probing with photons. Unfortunately, all this method is reduced to the few electron volt range what we can obtain at first in one measurement. So this is really the disadvantage properties of the photon probing. For it need either the small absorption sample or large absorption sample, so we cannot investigate all samples in one technique. Maybe recently, most frequently, we can use the spectroscopic ellipsometry. This is nowadays widely used, but the main problem is that during the evaluation, we can have the strong estimation of the dispersion relation. So we have to know the dispersion relation in advance in analysis. So all this has disadvantage. Let's see if we try to probe the sample with electrons. Let's first the transmission mode. It is very excellent technique, but we really need high energy electrons. So it means several 10 times of 10 keV electrons, so maybe 40 keV electrons or even higher energy to investigate the sample. Also, we need a very careful preparation of the samples, which is maybe studies work, using the thin films. What about the reflection mode? So in principle, we can investigate the processes at much lower energies in a kilo electron volt range. We may have a large scattering angle to analyze the reflection electron, or advantage of the reflection electron energy loss spectroscopy spectra. But what we have both excitation on surfaces and bulk, and also we have a multiple scattering effect. But what is the advantage of this technique? That we can evaluate the data at a really larger energy loss range. Here I just mentioned 0 to 100 electron volt, but recently in our investigation we practically use till at least 200 electron volts. At first, I would like to just refresh what is a Monte Carlo technique and how we can obtain the spectra, what we can able to measure. I call it direct Monte Carlo simulation. What is direct Monte Carlo simulation? We have a sample here. Maybe we have a bulk, we have a surface. We irradiate the sample with electrons, so we have an electron gun. From the electron gun, we have a few keV electrons, and penetrate into the sample, and after some motion inside the solid, the electron can escape from the surface and from the bulk, and we can able to measure the electron spectra with a different kind of technique. So how it looks like, here is a schematic diagram what we have to follow. So during the simulation, we can take into account both the primary reflected electrons and also the secondary electrons. And from this, we can mimic the experimental data. How we can do it? As I mentioned, the two main processes here is the elastic scattering and the inelastic scattering. For the inelastic scattering, we use a partial wave expansion method, which we think recently is the most accurate way to calculate elastic cross-section, both the differential elastic cross-section and the total elastic cross-sections. During the years, we also think that the most accurate way to calculate the inelastic scattering process is using the dielectric response theory. In this case, we have a dielectric function, which is depend on the momentum transfer and energy transfer. And in this simple way, we can calculate the bulk excitation and surface excitation. How looks like this function, I will show you later. So it is this is a very complex form to write it down, the inelastic cross-section, but later on I will show you that how we can really calculate. So the calculation process is just a simplified version of the Monte Carlo simulation. At first, we can able to calculate the cross-sections. We are not need to calculate during the simulation. Otherwise, this is really time-consuming simulation if we follow millions of electrons to get the spectra. So we have to know the differential, elastic, differential, inelastic cross-section. We have to know the total cross-section. The total cross-section will give a form to calculate a given distance between the two scattering process, and practically we follow the zigzag trajectory inside the solid. How it looks like a real spectra, just a simple example from my really old work. I would like to show how it looks like the inelastic spectra reflected back from the silver sample. It is just a testing of the dielectric function formally, because the dotted line came from the single scattering events from the Monte Carlo simulation, and we can able to calculate analytically this cross-section for a first scattering, and this is a red line. As you can see, it's really pretty well. Now, how it looks like if you would like to mimic the inelastic cross-section, inelastic peaks from the silver. Here, I would like to show some results from 2 keV energies. The green points is the experimental data. And if you take into account only the bulk properties of the sample, we can simulate the spectra and we can obtain the blue lines. As you can see, there is a huge difference between the simulated data and the experimental data. However, if we can do some crude approximation that the first three layers, we can characterize the surface properties of the material, and we can repeat the simulation. We can obtain the red curves, and for the case of 2 keV energy, we can get a really nice agreement with the experimental data, although we are using the very crude approximation of the sample. But if we repeat this at lower energies, at 200 eV, the situation is the same. If we can take into account only the bulk properties, we have large differences between the experimental data and between the calculated data and the experimental data. If we use this 3-steps model of the sample, we can improve the agreement between experimental data and the calculation, but at low energy, and still not reasonably good. So, what is the conclusion? If we would like to directly simulate the real spectra, we need to mimic the multiple scattering effect, the surface excitation, and we have to also take into account correctly the experimental conditions. Here, I would like to show some other example of the multiple scattering and surface, how we can take into account surface excitation and multiple scattering with a very, very easy material, let's put it that way, taking into account just the silicon, because the silicon has very simple energy loss function indicated here in this picture in the right-hand side panel. If we use this loss function and we mimic the reflected energy loss spectroscopy spectra for different energies, we can obtain the effect of the multiple scattering. So these are multiple plasmon excitations here. This is practically the bulk plasmon excitation of the silicon. And here in this band, we can also see the surface excitation of the spectrum. So if we would like to obtain the optical data and we would like to do a really careful analysis of the real spectra, what we have to do, we have to remove all these effects from the spectra. So this was a case of the direct Monte Carlo simulation. And I promised you that I will show you some more accurate equation for inelastic cross-section. So this is a theoretical talk, but I do not want to show in details how we can calculate. But if you remember, it was very simple form of the inelastic cross-section, but in real case, we have to calculate this equation if we would like to obtain the inelastic cross-section. This is above the surface, and this is in the surface. And as I mentioned, if we have a correct way and correct energy loss function, we can able to accurately simulate the experimental data. Here, just the example when we use a nickel sample and we use the optimized energy loss function. As you can see, for 1, 2, and 3 keV, we have really perfect agreement with experimental data and simulated data. However, I mentioned that in this case, we really use the best optical data what we can able to find in the market. This is our calculated data. I will show you later. So what we can say, if we have a correct energy loss function, we can really get a high accuracy simulation of the real spectra. So the idea, the brilliant idea of the Chinese colleague was that if this is a case, why we do not use this technique? So because the experimental data contain all information of the sample, so we have to use accurate experimental data, and maybe we can able to obtain very high accuracy optical data from the measurement. What we need a really high accurate measurement of the reflected energy loss spectroscopy spectra, and from the spectra we can obtain the the energy loss function, and from the energy loss function we can obtain the optical data. And therefore, we name this technique as reverse Monte Carlo method to extract optical data. What does it mean? So, as I mentioned before, we need accurate measurement, and this measurement is the basement of the calculation. We use multiple other technique to optimize the parameter of the loss function. This is also not surprising that we have the excitation spectra, and the excitation spectra, each peak of the excitation spectra can be written in this form. So this is one peak in excitation spectra. We can use this kind of Drude linear type function to mimic the initial energy loss function. For a simple case, from simple elements like silicon or aluminum, we can have only few function, but for more complicated cases, we need maybe several 10 times of Drude function to write it down correctly, the energy loss function. As you can see, each Drude function has 3 parameters: is amplitude, the energy, and the width of the peak. And during the multiple optimization, we have to optimize these 3 parameters for each peak. So we can call it, we combine the Monte Carlo simulation of the real spectra with the Markov chain Monte Carlo method to obtain the parameters of the Drude functions. As I mentioned, the crucial point of the method is a good experimental data. As I mentioned, in Hungary, in Debrecen, we have a very excellent spectrometer. We call it ESHA-31 electron spectrometer. It can produce a really high quality real spectra. We have electron gun. We can clean the sample, and we can able to use this spectrometer to measure the real spectra. As an example, as a next example, let's see the case of iron. Iron is also very important materials in application point of view. And here are the real spectra for 3 different energies: is 500 electron volt, 1, 2, and 5 keV energies. During the simulation, this was a basement of the simulation. We would have liked to simulate this spectra accurately using the reverse Monte Carlo method. How accurate this method and how time-consuming is this method? So, as I mentioned, we are using a global optimization of the parameters. So, in this case, for the case of iron case, we finally obtained the good agreement with the experimental data for each energies. Roughly speaking, when we have 4,000 iterations. So 4,000 iteration, we can get the correct and very good agreement result with the experimental data. How we can obtain? So at first, at the 0 order, we obtain this data. So the black dots are the experimental data. The red ones are the Monte Carlo simulation. These are the direct Monte Carlo simulation using the given set of the parameters. And you can ask how we can select the first energy loss function. In principle, for the case of the method, this is independent how we can select the first energy loss function. But make life more easy, and maybe the calculation is more fast, we can, if we have a more and more accurate initial loss function, we can get the results more easily and using less step size. So what we did, we use optical data from the Polyg book, and if we set it up, this is the first result. And after sometimes after maybe 4,000 iteration, we can have this nice agreement with the experimental data. And in this case, we can say that the optical data or energy loss function, what we use during the simulation of this data, this is a correct optical data for a given material. What we can see and how we can check the accuracy of the calculation, we can check it with different sum rules. As you can see here, this is F sum rule and P sum rules. And I do not want to go into detail because maybe I have only just 1 minute, and I would like to show some other results. So here is a F sum rules, and F sum rules gives you the nuclear charge. In different way we can calculate, and also the P sum rules, the P sum rules, if we can calculate the nominal value of the P sum rule is a unit. And what we can see, here is the simulated data of the iron. Here is the loss function. And as we see, the method requests only one measurement, but we are physicists and we can learn in the first experimental class that one measurement is not measurement. So at least for each cases, we always repeat the measurement and the calculation at least 3 energies, and we average out the energy loss function. And from the, finally, we get the average energy loss function. We can say that this is a loss function of the given material. And in this panel, I would like to show you the previous energy loss function, and what we obtained is a red one, which we can say recently we believe that is the most accurate function of the iron. And as I mentioned, we can calculate from the loss function the optical constant N and K. Here in the middle part, even in the literature, we did not find any data. So from this analysis, we can obtain the optical data N and K from 0 to 200 keV. And here I would like to show you the results of the sum rules. Here are the P sum rules. Is nominal value is 1, so we are very close. The previous data gives this number, and F sum rules, the nominal values is 26, and here we obtain almost this 26. I still have a few more minutes. Just quickly, I would like to show you some other examples. As I show at first, here is a nickel case, but I show as an example how we can obtain the nickel loss function and how we can obtain these nice results with the experimental data. We use the same way, and the red curve gives the energy loss function of the nickel. You can say that this is accident, but I would like to show some other calculation results. This is the results of the N and K, and here is a certification of the results using the P sum rule and F sum rule. You can say that maybe this is accident and that we can obtain these nice results, but not. We so far performed the elements of the 1/3 of the periodic table, I think, and we can say that we have the same accurate results as we obtained for the nickel and iron case. As I mentioned, just in 1 minute, I would like to show you some other example for iridium case. Iridium is also a very important material, and we improve the energy loss function. And here I would like to show the N and K data. And 3 other example, chromium.
I'm so sorry, but you have only 1 minute.
Yes, I am close to finish. So the chromium data is here. I would like to show you the cobalt data. The cobalt data is here. And finally, the palladium data. I left the palladium at the end because, as you see, the energy loss function, we have a really large discrepancy between the previous data. And finally, we recommended the red curves. And I would like to summarize how it looks like the sum rules. Here are the P sum rules and F sum rules. And as you can see, the reverse Monte Carlo simulation data gives the most accurate results if we just see the sum rules results. And finally, I would like to conclude my results. So I hope I show you some new technique to obtain the optical data. And so far, we obtained, as I mentioned, maybe 1/3 of the periodic table and recalculated the optical data. And really, thank you very much for your attention.
Okay, thank you. And maybe one short question.
Karoli, thank you very much for a very nice talk. And my question is, how sensitive your technique to the surface contaminations?
It is, as you see, we are using the KV electrons in a measurement because the calculation, we are including both the surface and bulk excitation during the simulation, but if we use a relatively high energy in a measurement, the technique gives more easy results to obtain the optical data. Let's put it that way: if we are going down for 100 electron volts or 300 electron volts, the calculation procedure is more time consuming. Therefore, we prefer the KV electron range. So, but in one word, the technique is sensitive to the surface excitation. We have to take into account really carefully the surface excitation.
Okay, thank you. Let's thank the speaker again.
I have a question, please.
I'm so sorry, but we don't have time for any questions.
I am so sorry that I was a little bit too much.
Okay, thank you. The next talk, Vladimir Pavlovich Popov, defects in silicon and high-K dielectrics of soy and soft structures after swift high ions xenon and with implantation.
Thank you very much, Mr. Chairman, and I would like to thank the organizing committee for inviting me to present our results of collaboration between 4 organizations from Russia. This is Ryzhanov Institute of Semiconductor Physics, Valiev Institute of Physics and Technology, Moscow, National Novosibirsk Research Institute, Joint Institute of Nuclear Research in Dubna. These results was obtained during last 2 years, and it is my pleasure to present this outline of my talk, and I will start with the motivation. It is here. I'm not sure what happens. Okay. The motivation of my talk is the using of this kind of materials in very strong applications. And first of all, I would like to present the method of obtaining this kind of heterostructure. I mean, silicon on insulator and silicon on sapphire. It is a well-known method suggested more than 30 years ago by Michel Brel from Leti, Grenoble. It is so-called smart cut technology for exfoliation of thin film of oxygen dioxide and thin film of silicon together to the silicon substrate to create silicon on insulator substrate. 5 years later, we suggest our method for producing of this kind of structure without the barrier layer of silicon dioxide using the simple transfer in vacuum at increased temperature, only thin silicon layers. It allows us to use a different kind of covered materials on the silicon substrate, not only silicon dioxide, but also the different kind of high-K dielectrics deposited by atomic layer depositions with the equipment in the Valiev Institute of Physics and Technology. And 10 years ago, we also suggested to use the similar technique. It doesn't work. Yes, thank you. This is our technique to transferring the film of different semiconductor materials in the case of a very high difference in the coefficient of thermal expansion using the moderate temperature also in the vacuum and the different kind of interlayers and silicon dioxide, high-K dielectrics, metals in order to obtain the whole transfer. The application of these materials is well known because it is the main integral schemes for digital radio that we have, that all of us have these integral schemes in our smartphones, where they use digital radio to move in the network from one mobile station to another. But the disadvantage of these materials is the using of very high resistivity silicon, but even more, we should have the special polycrystalline layers in this substrate in order to decrease the lifetime of the carriers to rock at the frequency as high as 500 gigahertz. We suggested to use another technique with low resistivity substrate using the carbon and oxygen implantation to create locally high resistivity layers. It works very well, but it works very well for generating or for using in the case of microwave length waveguides and the optical wave gaps. But in order to transit to higher frequencies, we should use the substrate of sapphire, because in this case we have much lower parasitic capacitance, and also the increased heat sink that is very important in the case of high voltage applications. And but the main advantage is a very low leakage currents, because of all elements are isolated from each other. And you can see here our results of operating of ferroelectric transistor, and the temperature as high as 300 degrees Celsius. So another advantage of high-K dielectric for using them as buried oxide layers or interlayers in the case of silicon and sapphire is a very high radiation resistivity. You can see here the results from a Japan group for hafnia. You see that even the radiation at very high doses, higher than 20 megarad in the case of gamma irradiation, and even 100 gigarad, only the defects generate at the interface due to the existence of interlayer of silica between the silicon and between the high-K dielectrics. No other defects create in this experiment. And the question for us was how these defects will be introduced during the using focused beam from electron microscope to obtain the very high dose of irradiation. It is very important for the space application, especially in the case of nuclear engine for deep space application, because in this case you could not have a large shield to save your electronic in safely position. And in the case of high-K dielectrics, we can use the doses as high as 10 or even more dose of gamma irradiation. And another very important thing is the using of so-called nanosheet or gate-all-around transistors, where we have only the electric field from the charge in this dielectric, in the charge, gate charge from the charge in the gate dielectrics, and no more. But in the case of the deep space application, we also should take into account swift heavy ions, because you can see from this picture in the middle that for this space application, galactic particles are very important, and this is also the same kind of irradiation that can destroy completely the active elements in your integral schemes. Something wrong, please. Okay. It was shown recently by a group from Dresden Technical University that the hafnia oxide is very stable for using in static random access memories, and also for using them in the case of ferroelectric random access memory, because it allows to use very high dose of swift heavy ions. In this case, it was gold ions with the dose as high as 5 to 10 to power of tenths per square centimeter, and you see that these devices still operate. The main defects after such kind of irradiation is the formation of tracks, but not in all solids. It is very surprising from the investigators that some materials like diamond, silicon, germanium, gold, silver, copper does not form the tracks that can be observable by using the simple method of investigation, structural investigation. But the defects generated, this is example of silicon on insulator, where using by simple stream estimation, the others used only nuclear stopping power, and you can see that experimentally determined cross-section for single event upsets is even lower than the predicted by this simulation when we take into account only the elastic scattering processes. And the question, what happens, and we had yesterday very nice talk of Roman Voronkov, who presents that even in the case of semiconductor or dielectric, we have very high level of electronic excitation, and this electronic excitation, like the pair of electron and holes, can seriously decrease of the number of defects that create in these materials. But some cases we can observe these defects by electron microscope and few nanometer diameter. The question for us was what happens in the case of very thin layer, because it is well known that the defects near the surface is more easily can be observed, and in the case of the interface, there are the same questions. I suppose to hear tomorrow the presentation of Rimzhanov about the interface defects. It's still interesting for our devices where we have a few 10 nanometers of silicon or and silicon and Gafnia layers in our structures. But according to the previous investigation of our co-authors Vladimir Skuratov from Dubna, it was shown that in the case of irradiation of xenon, of alumina, we can observe the formation of the track with a diameter 1.7 nanometer, and in the case of bismuth irradiation, we can see 2 times higher irradiation, 2 times higher in diameter the tracks. But the relation between electronic stopping power is only 1.6, not 4, as in the case of these defects. Moreover, there is a threshold voltage for obtaining this kind of tracks in this dielectric, and the threshold, not voltage, the threshold electronic stopping power is about 10 keV per nanometer. And it was shown in many experiments, but for the case of silicon irradiation in the single ion, in the heavy single ions, even in the case of uranium, we cannot see these defects immediately in the silicon. You see here the comparison of formation of this kind of tracks. In the case of Fullerene irradiation, is the same electronic stopping power as in case of the xenon. We cannot see in silicon nothing for the case of xenon, but in the case of silicon, we can observe this track, and the radius of this track coincide very well with the thermal spike model, with the quadratic dependence on the energy loss for electron excitations. And the questions for us, the first question for us, can we observe the latent track in our ultra-thin silicon layers in our structures? Another very interesting question about the phase transition in the dielectric, because as you remember, in the case of the diamond, we also can observe the formation of the track, but in the case only when we have the phase transition from diamond to graphite. In the case of irradiation of hafnia, we can see the ferroelectric hysteresis, which only decreased during the duration. But after the switching this dielectric, we can observe the same others from Dresden University can observe the formation after heavy ion irradiation. They can observe the transition from monoclinic red color to the orthorhombic phase. But firstly, this transition observed to the cubic phase. The second question for us was, if you will have initially cubic phase, can be observed the transition from cubic to orthorhombic phase immediately after this irradiation? In the case of epitaxially grown silicon layers, thin silicon layers on the sapphire, there are a lot of the extended defects. There's reason dislocation mainly, and all some polycrystalline structure near the interface. But in the case of our transfer technique on sapphire, you can see that without interlayer, with silica interlayer or with hafnia interlayer, we cannot see any extended defects, or very rarely observed some of the dislocations. Moreover, in the case of hafnia doped with alumina, we can see the formation of not only monoclinic phase, but also the orthorhombic phase directly, and it is also coincide with our electrical measurement. But first of all, I would like to mention that in our SOS structures, we have extremely high level of the stress, about 1.3 gigapascals. And it depends strongly on the using of the different kind of interlayers. We can change these stresses by measured by Raman spectroscopy, simply by the peak of single phonon scattering at 520 reverse centimeters, and we can regulate this one by using the xenon or bismuth irradiations. But we use the special regime where we have only single ion tracks without their overlapping to obtain the dependence on the electric stopping powers. Firstly, we've used the pure monoclinic phase according to Glenn incident X-ray diffraction, and we see here the transfer curve and this quite clear signature ferroelectric behavior in these pseudo-MOS transistors, and we can obtain the different parameters, density of states, charge in the interlayer, and also the mobility of our electrons and holes. But in the case of when we use the epithermal annealing to form the previously cubic phase of hafnia, we also can observe the transformation of this phase during the irradiation or during the heating for thinning to few nanometer thickness in the silica layers. You see that in all these cases, we have the same ferroelectric hysteresis, and after the feeding procedure, due to very high temperature of oxidation at 1100 degrees C, we observed of reversible order in the transfer curve that allows us to conclude about the loss of ferroelectricity in our films. The electrical parameters are presented in the table. It's very nice parameters for different kind of application. By returning to the radiation stability, we also using the focused ion beam to irradiate our samples with the electrons focused beam with density about 100 kiloamps per square centimeter. And you see here that accumulation of the positive charge moves the threshold for these transistors to the left side due to the positive accumulation in the case of silica. But in the case of high K dielectric, we could not see this shift. And about the same situation we observed in the case of irradiation with xenon or bismuth. In this case, you can see that we also observed the introduction of positive charge in this dielectric because the cubic Gaussian gave us a large negative charge for transistors, and this charge is dimensioned, but the relation between the change in this charge is equally low, is equal to the 4. It means that the track in the dielectric is the main source of the defects in the case of Hafnia. But I should also mention that the resistivity changed about 20 times for xenon irradiation and about 1,000 times in the case of bismuth irradiation. But we can change the temperature of our transistor in a wide interval of temperatures up to 300 degrees of Celsius, and it allows us to obtain the situation when we can measure only the defect introduced in the latent track, because the self-conductivity of silicon is about the same for 250 degrees of Celsius, and we can compare the resistivity of our pseudo-MOSFET channel. It is 0.7. It is equal to the relation between electronic stopping power for bismuth and xenon ions. This is the results of our measurements. I'm awfully sorry for this picture because the quality is very worse, and it is due to the relatively strong influences of these devices using the temperature irradiation, using the temperature treatment, using the different kind of explosive lithography methods. It's not so convenient for this kind of materials. But we see here that the relation between the change in the stresses in these materials is also equal 1.7. That means that in silicon, we have only influence of the point defects, not the latent track influence. It is the same as the change in the resistivity of our materials. And finally, I would like to present the results of using different kind of silicon on insulator samples with different buried oxide layers. Here it was shown for 20 nanometers high K buried oxides, but really we works with from 5 to 20 nanometers of the thickness, and the results strongly depends not only on the ion type but also on the resistivity of our on the type of resistivity of our substrate. You see here the results that was initial shown for ferroelectric switching of our transistor, pseudo MOSFET transistor with orthorhombic phase, and after the irradiation we can measure the characteristic of only across the whole structure, because the leakage currents due to the track formation in these ultra-thin buried oxide layers is very high. But it was surprising for us that in the case of N-type silicon films, P-type dielectric, we still can observe the working of our PN junction or ferroelectric tunnel junction transistors that can be operating very high space surroundings, not only for gamma irradiation but also for very high heavy ions. And these FTG devices can operate even in the case of high dose swift heavy ions. So in conclusion, the answer on the first question about the latent track generation in our thin film silicon devices, that the point defects is the main defects after this kind of irradiation, but the generation of positive charge is connected with the tracks at the interface with our interlace high K dielectrics. We can control the stresses is our SOI and source structure using not only different interlayers but also by using xenon or bismuth irradiation. It will be operated, and the answer about the possibility transition from cubic to orthorhombic phase show us that we could not see this kind of the transition immediately after irradiation. And tunnel junction diodes is the best choice for these applications in deep space missions. Thank you for your attention, and our thanks to our collaborator from our organization and Russian Scientific Foundation grant for financial support. Thank you for your attention.
Yes, thank you. Questions?
Yeah, I have a question on possible annealing of the defects you have created with the irradiation with the bismuth or xenon. How stable the defects are, and what is the effect of the annealing on your structures?
Do you mean the results of annealing after irradiation? We still don't use these devices for irradiation because our plan was an investigation of high-resolution transmission electron microscopy, and we still await the results for this one. And after that, we will do these annealing experiments. But I should mention that in the case of xenon irradiation, we practically do not see any large difference between initial one and irradiated samples, only 20 times higher the resistivity. This is the main results. No degradation of mobility, no degradation of the interface states density.
But in this case, you adduced that deteriorate the properties, but what is the influence of the irradiation?
What do you mean?
What is the influence of the irradiation? Why do you have so high?
In the case of xenon irradiation,
yeah.
In the case of xenon irradiation, we've observed only a small change in the initial negative charge near the 6 to 10 to power minus near the 7 to 10 to power 11, and after that we see that the charge near the 6.3 to 10 to 11 only. This means that we have no higher than about 7 to 10 to 10 the positive charge introduced after the irradiation in the interlayer. This is effective charge. It is the charge between the charge effective charge near the interface that influence on the threshold voltage of our transistors.
Yeah. Okay.
Any more? Okay, I have a question about the memory structures. Do you have experiments of irradiation of memory structures with some kind of ions, maybe other kinds of irradiation?
Unfortunately, no other production of similar type of SOI or maybe SOS devices with this kind of high K dielectrics. We still need to work to introduce this structure in the production plane for different kind of application, because we work usually with very thin silicon layers, few 10 nanometers for silicon and about few nanometers. In the case of high K dielectrics, it's not so easy to use in the modern productivity lines.
Okay. Any more? Okay.
One question, yes. And the last row.
Simple question. What is the reason for choice of such science? Xenon 26, bismuth 41.
Simple. The source in Dubna on the cyclotron U400. It's the simple the source of these ions. It is not connected with some kind of galactic race. It's only the it's only the well investigated Swift heavy ions. We can see a lot of publication on this theme to compare with our results.
Thanks. Okay, let's thank the speaker again. And the next talk, Alexander Yakovlevich Polyakov, hydrogen plasma influence on electrical properties and deep trap spectra of various polymorphs of gallium oxide.
Yeah.
Так, добрый день. Меня зовут Александр Поляков. Я сегодня буду говорить о том, какое влияние оказывает обработка в водородной плазме на свойства различных полиморфов оксида галлия. Значит, работа выполнена большим коллективом людей. Это группа моя, которая работает в университете МИСИС. Затем это группа Владимира Николаева, которая занимается ростом метастабильных полиморфов. Это Андрей Мяконьких, который нам любезно проводил эти самые обработки в водородной плазме, он из ФТИАН. И, значит, Андрей Кузнецов и Александр Азаров из университета Осло, которые для нас сделали образцы гамма-полиморфа, про которые я еще буду говорить. И, наконец, значит, профессор Инхван Ли из университета Корея в Сеуле, который очень помог нам с улучшением свойств капа-полиморфа, и профессор Пиртон, который провел много расчетов для нас и руководил тем, чтобы, значит, сделать измерение профилей Симс. Так. Кажется, так. Ну ладно, на самом деле это не так важно, потому что там была картинка, которая изображала, какой важный материал оксид галлия. Да, вот это, да, наконец. Какой важный материал оксид галлия, вы про это сегодня уже много слышали, и я ее показываю, ну, так сказать, в ритуальных целях. Значит, мы изучаем 4 важных полиморфа оксида галлия. Широкозонный материал оксид галлия имеет много полиморфов, но это вот 4, которые на самом деле более-менее представляют интерес для разных практических вещей. Самый главный, конечно же, это, значит, стабильный моноклинный бета-полиморф, из которого делают все чудесные вещи, которые сейчас пытаются, в общем-то, продвинуть в практическую жизнь. Затем второе, пожалуй, по важности занимает место альфа-полиморф. Это полиморф, который устойчив до температур, ну, порядка 600 градусов Цельсия, но имеет большие преимущества. Я про них... не слышно? Я про них буду говорить, когда буду говорить про альфа-политип. Значит, третий полиморф, про который мы будем говорить подробно, это, ну, здесь он назван эпсилон, на самом деле его правильно называть капа, это орторомбический полиморф. И, наконец, гамма-фаза – это, значит, полиморф, который имеет кубическую структуру, здесь дефектной шпинели, и, значит, интерес наш к этим структурам несколько различен, но все они в общем-то, представляет интерес и для практики, и для физики полупроводников. Итак, значит, понятное дело, что больше всего изучены свойства водорода в бета-галлий-2О3. И здесь проведены теоретические расчеты, которые показали, что межузельный водород – это мелкий донор, который очень подвижен. Значит, если он оказывается вблизи мелких доноров другого типа, то он может превратиться в мелкий акцептор, может превратиться в акцептор со свойствами отрицательного negative U и образовывать комплексы с такими донорами. Значит, кроме того, он может образовывать комплексы с донорами, вакансиями кислорода, которых в бета-галлий-2О3 3 типа, но фактически это некое смещенное положение водорода по отношению к его узельному положению, когда он замещал бы кислород. И, значит, здесь в этой малосимметричной системе есть 3 положения кислорода, и 2 из них при взаимодействии с водородом дают мелкий донор, а одно создает центр с отрицательной корреляционной энергией. Его энергия, его уровень около 0,6 электрон от края зоны проводимости. И все эти штуки очень подвижны. Значит, дальше, пожалуй, главным дефектом, который в большой концентрации встречается в оксиде галлия, это вакансии галлия. Вакансии галлия – это трикратно заряженные акцепторы. И расчет DFT показывает, что обычно в оксиде галлия это не просто вакансии галлия, а расщепленные вакансии галлия, то есть это некая комбинация вакансий галлия с межузельным галлием. Их, естественно, в этой малосимметричной системе 4 типа, но, значит, сейчас не будем на это заострять внимание. Была довольно подробно изучена теоретически подвижность, теоретически экспериментально подвижность водорода в оксиде галлия бета-полиморфа. И при этом выяснилось, что, значит, если вы пытаетесь ввести водород из плазмы, то это оказывается очень трудно, если вы на поверхности с помощью плазмы не создаете дефекты, к которым водород мог бы прилепиться и потом скакать по ним, перемещаясь внутрь образца. При этом, значит, скорость диффузии сильно анизотропна, она очень большая, ну, относительно большая, тогда, когда у вас ориентация 0,1,0, и это связано с тем, что у вас есть каналы с малой плотностью атомов, которые идут внутрь кристалла от этой плоскости. Тогда же, когда у вас ориентация минус 2,01 и другие на самом деле, то таких каналов нету, и, соответственно, скорость движения водорода достаточно низкая. Что ж такое? Что? Вот я. Окей, good. Значит, образцы, которые мы изучали в этой работе, это были кристаллы бета-галлий-2О3 и пленки, выращенные на подложках галлий-2О3. Это коммерческий материал, который производит Tamura Novel Crystals. И, кроме того, все метастабильные полиморфы альфа и капа были выращены методом хлоридипитаксии, но в разных условиях, на разных подложках. Значит, гамма приготовлена была с помощью имплантации галлия с энергией 1,7 мегаэлектрон-вольт в бета-галлий-2О3, компенсированная железом. И, кроме того, часть образцов были дополнительно имплантированы кремнием, и некоторые из них были отожжены. Последние измерения были проведены в университете Осло. Ну, значит, по поводу этих вещей, почему это вызвало интерес? Потому что наши коллеги из Осло сделали великое открытие, которое заключается в том, что когда вы создаете такую структуру, то в ней на поверхности образуется гамма-фаза, и оказывается, что такая структура необыкновенно устойчива к аморфизации. То есть вы можете там создавать огромные потоки значит, облучения для такой структуры, не наблюдать аморфизации. Более того, если вы будете смотреть на рентгеновские данные, на значит, просвечивающую электронную микроскопию, то тоже ничего особенно не видно. Значит, казалось бы, это хорошее свойство у материала, но, естественно, нужно было бы понять, значит, вообще для чего-нибудь другого, кроме того, чтобы написать об этом статью в Nature, значит, годится ли это или нет. Значит, и для этого нужно было провести электрические измерения, узнать, что за свойства у этого чудовища. Мы попробовали это сделать. Значит, плазму мы использовали с индукционной связью. Это промышленный реактор. Обработка проводилась при 330 градусах Цельсия в течение 30 минут. И, значит, при большой мощности плазмы и при большой мощности, значит, сообщаемой ионом, при большом напряжении, которое подается на очаг вашей структуры, для того, чтобы создать ионы, которые бомбардируют поверхность всерьез. Значит, что такое? Ну, что такое? По поводу взаимодействия вакансий галлия с водородом. Значит, некоторая суета вокруг дивана началась тогда, когда американская группа исследователей рассказала, что они умеют получать на поверхности бета-галлий-2O3 пленки либо N-типа, либо P-типа, в зависимости от того, какая была подготовка поверхности. Если они создавали большую концентрацию вакансий галлия и обрабатывали этот материал в ампуле при 900 градусах Цельсия в молекулярном водороде, то они получали, значит, материал P-типа. Естественно, все возбудились и, значит, бросились вдогонку. Я не видел никаких экспериментальных подтверждений из других групп, которые показали, что такая вещь наблюдается. Но, значит, рациональное зерно здесь… и, значит, кроме того, если концентрация вакансий была маленькая, а концентрация водорода была большая, то тогда они получили материал N-типа. И здесь, значит, все понятно, потому что они утверждают, и это действительно подтверждается другими людьми, что, значит, вакансия галлия может связать до 4 ионов водорода, и тогда, когда она связывает 4 иона водорода, то тогда, значит, она превращается в мелкий донор. Они работали с обычными вакансиями галлия, но сейчас показано, что и для растянутых вакансий это такие же вещи. Значит, тогда можно себе думать, что таким образом можно было бы попробовать получить материал P-типа. Мы попробовали это сделать с помощью обработки в плазме и выяснили неприятную вещь, значит, что огромная анизотропия эффекта. Если вы работаете с плоскостью 0,1,0, то такая обработка приводит к тому, что у вас материал становится более высокоомным. Если вы работаете с материалом -2,0,1, то, значит, при этом у вас концентрация электронов на поверхности сильно возрастает. Значит, мы попытались про это что-то понять, я сейчас про это буду говорить. Но ключевой фактор здесь такой, что, значит, диффузия анизотропна. И таким образом, значит, если вы создаете на поверхности много дефектов, и эта поверхность такая, что эти дефекты могут легко проникать в глубину, то тогда в глубину будет проникать и ваш водород, он будет... Что же такое? Ну, какой-то... Вот. Он будет показывать профили вроде тех, которые показаны на верхнем слайде, они получены с помощью имплантации, но, значит, имплантации потом разгона водорода. Значит, и эти профили, они типичны для движения водорода в полупроводниках и связаны с тем, что водород захватывается на какие-то глубокие, на какие-то центры, на которых он сидит, и отпускается, и таким образом прыжками двигается в материале. При этом, значит, эта скорость движения, она большая для материала с ориентацией 0,1,0 и маленькая для материала с ориентацией -2,0,1. Ну и здесь показаны эти профили, и здесь что мы видим? Мы видим, что когда мы используем плотную плазму, то тогда профили вполне себе измеримые, изменения, значит, электрических свойств большие. Тогда же, когда мы работаем в плазме, в которой, значит, поверхностные дефекты не создаются, проникновение водорода достаточно хилое. Значит, что тогда мы решили сделать? Мы решили посмотреть, что же эта самая страшная плазма дальше делает. Ну что за... Нет какой-то. Ну, это...
Смотрите.
Да.
Вот это большая вперед, вот это назад.
Окей.
Другие не нажимайте.
Хорошо.
Ладно, давайте я пощелкаю.
Давайте. Извините за бестолковость. Да, следующий. Итак, значит, начнем с этого слайда, где мы показываем, как меняется концентрация носителей, которые мы измеряем вольфорадными измерениями, и как изменяется спектр глубоких центров тогда, когда мы обрабатываем в водородной плазме объемные кристаллы бета-галлий-2O3 N-типа с одной и той же исходной концентрацией электронов и с похожими спектрами глубоких центров. Значит, у нас ориентации 0,1,0 и -2,0,1. Начнем с ориентации 0,1,0. Значит, это правый слайд. Мы видим, что начальная концентрация была под 2 на 10^17. После обработки в плазме она уменьшилась до примерно 10^16 на глубину порядка 1 микрона. Если мы посмотрим на спектр глубоких центров, то, значит, доминирующими центрами являются так называемый центр Е2. Это центр с глубиной около 0,8 электрон-вольт от края зоны проводимости. И это центры, связанные с акцепторами железа. И центры Е3 – это глубокие доноры, которые, значит, имеют энергию активации около 1 электронвольта. После того, как мы такой образец обработали в водородной плазме, мы видим, что никакого центра Е2 не осталось вообще. Вместо него возник другой центр Е2 со звездой. Это центр хорошо известный, это центр, который на основании некоторых модельных расчетов приписывается дивакансиям галлия и кислорода, и который, возможно, связан с водородом. И возникает еще центр Е1, который тоже, как выясняется, связан с образованием комплекса с участием водорода, и, значит, центр, который является радиационным дефектом, Е7. Если посмотреть на другие образцы, ну, значит, его брат-близнец – это образец, который изображен с левой стороны, и для него что мы видим? У него ориентация -2,01, и когда мы его обрабатываем в плазме, то мы видим, что в нем концентрация сильно возросла, до там выше, чем 10/18 на сантиметр -3. Значит, спектр… Что вы? Спектр в нем был такой же, как и в образце, который мы только что обсуждали, и точно так же в нем пропал центр Е2, а появился центр Е2 со звездой. И появилось широкое плечо, которое, значит, бесструктурное, которое связано с сочетанием большой концентрации различных дефектов сравнительно мелких. Похожий образец нарисован справа, отличается он только тем, что его перед тем, как мы его, значит, начали мучить, его еще мучили наши норвежские друзья, обработав его в молекулярном водороде при высокой температуре 900 градусов Цельсия. Значит, и это привело к тому, что в нем вот возник этот самый центр Е1, который является комплексом с водородом. Тем не менее, значит, акцепторы, связанные с железом, при этом не исчезли. Тогда, когда мы обработали эту штукотень в водородной плазме, то мы увидели, что никакого железного центра нету, появился сильный центр Е2 со звездой и, значит, бесструктурная полоса очень высокой интенсивности при низких температурах. Значит, с чем это связано? С тем, что в одном случае у нас водорода много, вакансий галлия мало, и, соответственно, получается много центров, соединяющихся с 4 атомами водорода, и получаются доноры. А в другом случае у нас вакансий галлия много, водорода мало, и тогда у вас получается акцептор. Следующий, да. Значит, никакого П-типа мы при этом, естественно, обнаружить не сумели. Мы подумали себе, что, может быть, это потому, что у нас слишком мало вакансий галлия. Поэтому взяли образец бета, на этот раз эпитаксиальный, с ориентацией 0,01, значит, и облучили его кислородом с большой энергией, значит, при этом в надежде на то, что мы создадим вакансии галлия, потом обработаем эту штукотень в водороде и получим себе, значит, П-тип. Вместо этого что у нас получилось? У нас получилось, что материал после такой обработки оставался бета-политипом, значит, полуширина кривой качания несколько возросла, полуширина кривой качания несколько возросла, но ничего ужасного не произошло. Значит, да, дальше, если... Так, значит, дальше что мы видим? Мы видим, что сразу после обработки в кислороде образец становится изолирующим до глубины 1,4 микрона, что соответствует примерно, значит, глубине, на которую его должны были пассивировать образовавшийся радиационный дефект. Значит, это квази-МДП-структура, до которой мы сделали измерение спектров глубоких центров. Значит, в исходном состоянии в спектре ДЛТС мы видели, значит, спектр, в котором преобладали состояние Е2 со звездой, Е2 железо и, значит, Е3. После того, как мы облучили эту штукотень, мы увидели, что у нас преобладающими центрами, значит, стали состояния Е3, и появились радиационные дефекты, вот этот самый Е8-029 электрон-вольт. Дальше мы обработали эту штукотень в водородной плазме. Значит, что при этом мы увидели? Мы увидели, что на поверхности появилась большая концентрация доноров, около 10-17. Этот профиль достаточно мелкий, концентрация достаточно быстро спадает, то есть у нас водорода явно недостаточно для того, чтобы, значит, закомпенсировать. У нас водорода становится достаточно для того, чтобы закомпенсировать наши эти самые вакансии галлия до состояния синего цвета, когда они становятся четырехкратно заряженными и создают доноры. Значит, при этом мы видим, что у нас в спектре ДЛТС это черная кривая наверху, там в спектре ДЛТС у нас появляется очень большая концентрация центров Е2 со звездой, большая концентрация, значит, этих самых центров Е3, и, значит, появляются центры, связанные, которые мы можем назвать Е1, значит, которые все они как будто бы могли бы быть связаны с водородом. Значит, важный факт здесь какой? Мы посмотрели на спектры фотоемкости. В этих спектрах, значит, в исходном образце имеются центры, у которых пороговая энергия ионизации 1,3 электрон-вольта, и концентрация довольно маленькая. После облучения мы видим, что возникла очень интенсивная полоса с энергией около 2,3 электрон-вольта, которая достаточно убедительно присуждена этим самым вакансиям галлия растянута. После того, как мы обработали это все в водородной плазме, мы видим, что эти центры, которые связаны со свободными вакансиями галлия, исчезли просто навовсе, нету их вообще. Итак, значит, если суммировать то, что мы узнали о бета, мы видим, что, по-видимому, это модель, в которой главную роль играют, значит, то, какие типы комплексов образуются с вакансиями галлия, она достаточно, в общем-то, убедительна. Возможно ли в такой ситуации получение P-типа, но не случайным образом, это довольно спорный вопрос, потому что вам нужно соблюсти строгий баланс между тем, сколько вы вакансий галлия создаете и сколько вы пассивируете их с помощью водорода. Ну хорошо, перейдем, значит, дальше к материалу N-типа, к материалу альфа. Я не буду говорить, почему он важный, хотя, значит, одна вещь, которую я скажу, это материал, на котором можно получить P-тип проводимости. Значит, и это было убедительно показано. Мы поговорим про это позже, потому что меня уже преследует наш руководитель. Но важно-то вот что. Значит, мы взяли материал, который выращен хлоридной эпитаксией, нелегированный. Следующий, если можно. Это материал, в котором уровень ферми около 0,6-0,8 электрон-вольт от края зоны проводимости. Он высокоомный, в нем мы видим глубокий центр 0,3, 0,6, 1 электрон-вольт. Значит, потом мы этот материал обрабатываем в водородной плазме. Следующий слайд. Lo and behold, что мы видим? Мы видим, что в материале появилась огромная емкость. Вольфарадное измерение показывает огромную концентрацию электронов, 10-19. Значит, когда вы остываете, то, значит, материал несколько вымораживается, но если вы посветите на него, то, значит, емкость восстанавливается и даже превосходит значения, которые были при комнатной температуре. И эти значения замороженные. Вы можете материал этот держать при низкой температуре сколько угодно времени, но, в общем, не скажу, что мы месяцами это делали, но часами это, значит, ничего не дает. А дальше вы можете его, значит, отогреть. И справа показано, что происходит, когда вы материал отогреваете. Значит, вы, значит, охладились. Это черные кривые, которые показывают, как меняется емкость от температуры для двух емкостей. Потом вы осветили образец, и, значит, вы видите, что только при температуре выше 400 градусов Кельвина у вас восстанавливается исходное состояние. То есть вы создали что-то такое похожее на DX-центры. Следующий слайд, если можно. Да? Это бог с ним. Значит, что здесь важно? Вы можете, вообще говоря, получить высокую концентрацию в альфа с помощью легирования оловом. Вот мы сравниваем то, что показывает образец, легированный оловом, и образец, который мы сделали с помощью обработки в плазме. В чем разница? В том, что в образце, обработанном плазмой, никаких центров глубоких, которые мы могли бы увидеть в ДЛТС, мы не видим. В образце, легированном оловом, их просто как грязи, там за 10⁻XVI на сантиметр кубический. Значит, в принципе, такая вещь была бы полезна для материала альфа, потому что это метастабильный материал, который на самом деле температуру выше 600 градусов Цельсия не выносит. И если вы хотите создать в нем высокую концентрацию носителей и сделать это локально, то этот метод на самом деле, в общем-то, мог бы пригодиться для того, чтобы сделать хороший амический контакт, например. Или, значит, слой, в котором у вас высокая концентрация носителей и нету глубоких центров. Следующий. Значит, капа. Капа – это материал, в котором у вас есть сильное поляризационное поле. И это очень полезно было бы, потому что тогда можно было бы делать поляризационное легирование, такое же, как в нитриде, галлия, и таким образом получать транзисторы с очень большой концентрацией двумерного электронного газа. Что этому мешает? Мешает этому то, что материал, когда вы его пытаетесь растить какими-то такими стандартными методами, предпочитает расти в виде, значит, ротационных доменов, которые вращаются на 120 градусов. И эти штукотения приводят к тому, что у вас имеется большая плотность дислокации между этими самыми доменами, и ток в плоскости вашего кристалла не течет. Значит, эту проблему японцы показали, что можно решить с помощью латерального эпитаксиального заращивания, которое иллюстрируется справа. И при этом выяснили, что, значит, вот в той области, которая называется окном в методе ИЛОК, у вас, значит, преобладает единственный домен. А вот в области между, значит, этими самыми окнами у вас имеется смесь доменов, такая же, как на левом слайде. Следующий. Значит, мы попробуем. Да, ну хорошо. Еще там 2 минуты дайте. Значит, что мы, значит, здесь выяснили? Мы такую же штукотень вырастили, японцы вырастили то, что вырастили, и потом не рассказали, какие у этого электрические свойства. Мы вырастили и рассказываем вам, какие электрические свойства. Когда вы такую структуру выращиваете, и она хорошо сращена, то, значит, следующий слайд покажите. Еще один. То у вас появляется, значит, гладкая поверхность. И если вы смотрите на нее в микрокатодолюминесценции, то вы видите, что там, где у вас окна в вашей структуре, не окна, а как, крылья в вашей структуре, крылья с низкой плотностью дислокации, у вас высокая интенсивность катодолюминесценции. Значит, мы попробовали эти штуки залегировать. Еще следующий. И еще следующий. Мы попробовали эти штуки залегировать с помощью олова. Выяснилось, вот, что Значит, олова можно ввести много, а концентрация получается низкая, ну там 10-13. Более того, значит, поскольку ток течет не одинаково, когда вы ставите ваши амические контакты параллельно вашим этим самым крыльям, и когда перпендикулярно, то у вас, значит, последовательность сопротивления сильно различная. Оно больше гораздо, когда вы ставите ваши контакты параллельно крыльям. То есть эти самые окна – это области, в которых низкая концентрация носителей. Значит, дальше мы обработали эту штукотень водородом. Следующий слайд. Увидели, что концентрация стала огромной, порядка 10-19. Увидели, что она точно так же заморожена в случае, как в случае с альфа, и увидели, что, значит, она показывает такие же свойства типа DX-центров, как и вот в случае альфа. Значит, скажу сразу, что такую же вещь мы увидели и на образцах, которые получены, значит, вот этим самым имплантацией галлия с преобразованием структуры в гамма-структуру. И когда мы обработали ее в водородной плазме, то мы получили очень похожие характеристики. То есть это некая общая характеристика оксида галлия. И тогда, значит, встает вопрос, а что это могли быть за дефекты? Значит, это должен быть либо, собственно, водород, либо какие-то комплексы, которые практически всегда и во всех структурах образуются. Значит, мы утверждаем, что это комплексы, значит, водорода с вакансиями галлия, и что эти комплексы обладают забавным свойством, что они являются DX-центрами. Ну и последнее, просто буквально 2 минуты, значит, по поводу того, каковы свойства этого самого гамма-политипа, который изготавливается. Если можно, вперед еще. Да, нет. Значит, мы посмотрели на этот материал в исходном там имплантированном состоянии, и в состоянии, которое достигается, когда вы, значит, обрабатываете материал до температуры там, порядка 600-700 градусов Цельсия, ничего хорошего там нет, они высокоомные, и ничего там вот прямо захватывающий дух не происходит. Значит, когда мы вводим туда водород, то материал становится проводящим. Проводящим, но довольно слабо проводящим. У него есть фоточувствительность, у него есть фотоемкость. Когда мы его облучаем протонами, то мы видим, что эти вещи изменяются достаточно низко, достаточно мало. Но здесь показано, как это происходит. Значит, почему есть такая разница между материалом, компенсированным облучением галлия, и компенсированным облучением кремнием, мы пока точно не знаем. Это какая-то вещь, которую мы изучаем. Я прошу прощения.
Все, спасибо. Давайте поблагодарим докладчика. Вот. И, наверное, вопросы давайте зададим на кофе-брейке. Время вышло. Сейчас кофе-брейк. Ну, коллеги, я предлагаю начать все-таки пораньше, да, и чуть-чуть мы пораньше закончим. Доклад сейчас будет представлять Михаил Овчинников. Эффекты микроструктуры углеродных материалов при ионно-лучевой модификации поверхности.
Good day, dear colleagues. The topic of my presentation, effects of the microstructure of carbon-based material under ion beam surface modification. Nowadays, carbon materials are used in various type of applications, and even more, they are promising in such areas like nuclear power plants as a moderator for high temperature reactors, for the space aircraft applications, for example, see on the pictures like the elements of the spaceships or the reflectors or heat shields. Also, they are promising carbon nanomaterials are promising in as a plasma electric applications in plasma electrolytic coatings and components of the fusion plants. Synthetic carbon materials have very based on the raw polymer material from which they are made of. From which they are produced. They have a different crystalline and supramolecular structure. So here we can see that for highly oriented periodic graphites on the top left, the crystalline sizes are about sub-micrometer sizes. And for the synthetic carbon, viscose-based carbon fibers, the crystalline size is about few nanometers. By the way, another difference in these materials is supramolecular structure. What is this? This structure is formed when the raw polymer material loses their organic compounds due to the processes of under the pressure of stretching and pyrolysis. And then the remain carbon atoms says their original structure. And this structure is different for the synthetic carbons. For example, for the highly oriented periodic graphite, they have graphite planes layout one on another. So this structure called lamellar structure. The PAN-based carbon fibers have another type of this structure, supramolecular structure, fibrous supramolecular structure. And for example, glassy carbons, so-called non-graphitizable carbons, so they're not graphitized up to temperatures 3000 Celsius. This structure called the globular with a characteristic global size about 5 nanometers. So based on this difference of these materials, it's very interesting to see how the high fluence ion beams can impact on the surface of these materials. And in this work, we made these experiments. So the experiments was performed on the Massman chromator of Skobelets Institute of Nuclear Physics with gallium and argon ions with the energy range from 10 to 30 keV. The other parameters of irradiation are listed in here, and the irradiation temperatures was from room temperature to 600 degrees. Surface analysis was performed using scanning electron microscopy, laser geniophotometry, and Raman spectroscopy at Raman excitation wavelengths 463 and 514 nanometers. The materials was used in this work is a highly oriented pyrolytic graphite, UPV-1T, high temperature glassy carbon, viscose-based carbon cloth, and pond-based carbon fibers, VMN4 in column. So a few words about the processes of appearance of the ion-induced morphology. It can be divided by two factors. First factor is the sputtering, ion-induced diffusion, and mass transfer. It's known as structures as ripples and others. So, but another type of ion-induced structures is uninduced plastic deformation processes, which induce these structures. For example, how in the right picture. So for the high fluence ion radiation, the main parameters of radiation-induced changes are displacement per atom and temperature. The amortization of carbon materials suppressed, then the temperature of irradiation higher than temperature of dynamic annealing of radiation damage. And then the amortization displacement per atoms goes to infinity, almost. So the suppression of amortization accumulate the accumulation of induced defects results in structural changes in graphite crystallites. They are twin, we are not bent, then they are rotating graphite plate one on each other. And this reveals of the much large number of the morphological changes of these materials. For example, here on a picture, they have a very wavy structure, and from transmission from microscopy, they show that these structures are made by just folding of the graphite crystallites. So here are results of our irradiation. Irradiation of highly oriented pyrolytic graphite results in splitting of graphite crystallites, and these flakes are oriented perpendicular to the surface. And on this back sizes of these flakes, they are covered with blisters. Irradiation of carbon fiber results in the same, probably in the same way, the shell of the carbon fiber split up, and they are oriented along to the fiber axis. We observed the formation of sub-nanometer size blisters on the surface of viscose-based carbon fibers, and they have no any morphological changes we observed on scanning electron microscopy on the glassy carbons. Compare this with 30 keV argon plus irradiation, we can see that the structure for highly oriented pyrolytic graphite and pond-based carbon fibers are quite the same in sizes. They have like some rigid structure. Some ridges are oriented along the certain direction, and this probably reflects the crystalline, the borders of the crystalline of initial non-radiated pyrolytic graphite. So for the viscose-based glass carbon fiber and glassy carbons, the structure is quite the same, and it's like the nanomesh surface morphology. In our previous research, we find that the depth of the maximum radiation damage its effect on the surface morphology. Here you can see that for Gillium and this comparison for the Gillium and argon ions. So then the maximum is in a depth of we observe the splitting of the carbon fiber shell. For the maximum of radiation damage is on the surface. We observe another topography like corrugation perpendicular to the fiber surface. So the same same like effect we observed on the surface of highly oriented periodic graphite. So we have for the highly oriented periodic graphite, we observe a splitting of graphite planes in a way very same as we see on a pan-based carbon fibers. Another interesting fact that the materials which are very different in initial materials that very different in crystalline sizes, highly oriented periodic graphites and glassy carbons, they have a very big difference in the crystalline size before radiation. And after radiation with the argon ions, they have a very similar structure, but with a difference in the sizes. Here the Raman spectroscopy of non-radiated and irradiated samples, and one can we conclude that the then we irradiate surface with argon or gallium ions with high temperatures, the structure have the similar disorder despite the radiation at room temperatures, and the surface is amortized. So here the conclusions of our work. We observed after this, we observed three types of morphology after radiation. It's a smooth surface, mesh-like surface, like the wall structure surface, and the corrugation of the surface. We also can conclude that the accumulation of induced defects results in the structural deformation of graphite crystallites. It's revealed in a similar way for the highly irradiated periodic graphite and the pan-based carbon fibers. Thank you for your attention.
Okay, thank you. Questions?
У меня несколько вопросов. Самый первый вопрос: я не понимаю цели работы, потому что углеродное волокно, как правило, обрабатывается для того, чтобы придать, изменить гидрофобность на гидрофильность. Достигается это с помощью именно как раз формирования перпендикулярных плоскостей углеродных. В чем ваша задача была?
Конкретно перпендикулярных плоскостей, скорее всего, нет. Дело в том, что по поводу создания конкретных композитов с помощью этих углеродных волокон может пригодиться как раз-таки наоборот, перпендикулярное гофрирование поверхности.
Расстрою, даже хорошо расстрою. Это давно известный прием, обрабатывается, как правило, плазма. Эти работы делаются в Ивановском технологическом университете. Углеродное волокно, кстати, не вискозное, это карбонизация гидроцеллюлозы. Вискоза — это из древесины делается. А из гидроцеллюлозы как раз карбонизует, получается углеродные волокна. То есть там свойства принципиально равные. И именно вот эти панволокно из гидроцеллюлозы обрабатываются с плазмой. как раз получение с изменением свойств с гидрофобности на гидрофильность, за тем, чтобы использовать уже для составления композитов. Что касается высокоориентированно-приоритического графита, здесь тоже, так сказать, эти все нюансы известны. Вот, то есть...
Ну,
я хочу понять, что нового.
А вот вопрос, прям вот изменение подобного типа рельефа волокна.
Да, совершенно верно.
Ну, я не знаком с этими работами, если вы могли бы авторов хотя бы подсказать, было бы интересно.
Смотрите журнал «Карбон» в первую очередь. Там очень много этих вещей.
Ну, хорошо.
Спасибо.
Еще вопросы? Okay, let's thank the speaker again. The next is Леон Богданович Бекрамбеков. Модификация структуры пиролитического графита и углеродных волокон под воздействием ионного облучения.
Добрый вечер. Вот это название доклада. Я так понял, что чтобы охватить большее число слушателей, я картинки нарисовал и подписал на английском, а говорить буду на русском. Этот доклад, ну, как видно, тоже продолжает тему предыдущего сообщения. Конечно, уже работа с моноатомными материалами имеет все меньшую, так сказать, аудиторию, все меньше людей занимаются. Теперь время многокомпонентных материалов. Но мне кажется, что все-таки углубление, так сказать, наших знаний проще как-то реализовать через лучшее понимание того, что происходит, когда однокомпонентная штука. Ну и вот, это некое извинение, что вот графит и все такое прочее. Ну вот, для чего он нужен, там и все такое, это, в общем, не так интересно. Вот на этой установке мы это изучали. Вот, вот это вот в середине плазма такая красная, оттуда ионы вырываются, фокусируются, облучают графит. Облучали при довольно высоких температурах, вот 2600 плюс-минус 50 Кельвина, да. Ну, для чего это? Вот, не буду я в это вдаваться, но, в общем, скажу, что при этом, конечно, диффузия уже углеродных атомов довольно мощная, да, и вся специфика вот этих пиролитического графита и вообще кристаллов графита, да, она проявляется очень явно. А специфика в том, что графит кристалл графита – это параллельные графеновые плоскости. Расстояние между атомами в каждой из этих плоскостей там примерно 2,5-3 ангстрема, а между двумя слоями 5 с хвостиком ангстрем. Поэтому диффузия вот поперек этих слоев, она заторможена очень сильно. И диффузия, и вакансий, и смещенных атомов фактически происходит только поперек. Да? И это вот определяет вот специфику этого материала, ну и его свойства. Значит, вот образцы пиролитического графита. Ну, пиролитический графит – это значит вот графит, у которого, кусок графита, у которого вот такие слои параллельные друг другу, но это не единый кристалл, а это мелкозернистая структура, состоит из зерен, но все эти зерна, они как-то повернуты вот в этом направлении, но у всех вот мы облучаем поверхность, на которой лежит вот эта графеновая плоскость, под ними другая и так далее. Да? Так что вот так. Облучали импульсами вот по 5 секунд, между импульсами 15 секунд, ну и смотрели, что получается, собственно говоря. Ну вот результат. Как там модифицируется все. Оказывается, довольно интересно. После 3 импульсов уже что получилось? Что вот этот самый слой, верхний слой. Ну, на самом деле, это не один графеновый слой, а их там штук 10-15. Ну, назовем их это верхним слоем. Он вдруг разделился, как бы растрескался, и у каждого этого кусочка края начали подниматься наверх. Так вот, заворачиваться. Когда прошло там уже там сколько, 15, по-моему, импульсов следующий. Это первый, да? А вот это когда 3 импульса. Вы видите, уже первый слой свернулся вот так. За ним второй слой начал сворачиваться. Ну и дальше и третий слой. Когда там прошло 15 этих самых импульсов, то вот, ну это вот ионное облучение, вот эта схема, как все это происходит, да, поднимаются эти слои. А когда их уже стало много, поднятых этих слоев, то видно, что уже поверхность не гладкая, она состоит вот из таких вот, ну, я не знаю, как луковица, да, по сути дела, но эти луковицы отделены друг от друга. Что, собственно, происходит, если возвращаться вот в первую, что получается? Мы облучаем ионами, ионы распыляют эту поверхность, да, то есть на этой поверхности расстояние между атомами, лежащими в этой плоскости, увеличивается. Естественно, они хотят сжаться, опять занять место, которое, так сказать, им уготовано, да, в кристалле. А как они могут сжаться? Их же следующие слои не дают им сжаться. Поэтому в этом случае природа находит выход, как избавиться от этих напряжений, которые там возникают. Эти слои сворачиваются. Когда этот слой так сворачивается, то оказывается в расстоянии вот этих составляющих, этих слоев, да, это расстояние меньше становится, то есть напряжение бывает. Ну, а у этих больше. И вот они сворачиваются первые. Ну, вот то, что я называю первым слоем, это примерно 10 слоев атомных. Следующие за ним сворачиваются. Когда теперь эти слои поднялись, стало возможным облучение следующих слоев. Они начали сворачиваться, следующие начали сворачиваться. И вот получилась такая луковица. А кроме того, когда мы выбивали атомы с верхних слоев, то здесь получались вакансии, оказывались, да, то есть расстояние между атомами увеличилось, как я сказал, но вакансии диффундируют, естественно, вот в этом слое и стекают на границу вот этого кусочка, да, а по сути дела это вот чаще всего тот самый один из кристалликов, а этот был другой кристаллик, третий. Когда они стекают на границу кристалликов, то оказывается, что расстояния между кристалликами появляются. И поэтому получается, что вот эти луковицы, они как бы отделены друг от друга. Довольно красиво, когда вот смотришь в микроскоп. Ну, и так дальше. Да. И вот, когда вот довольно уже много этих самых 18 циклов, да, то оказывается, что вот они все это сгибается. Раньше были заметны эти слои, под действием распыления сглаживаются, они менее заметны. Но видно, что вот на вершинах, да, ну, получается как бы конусы такие, да, конические штуки, или полосы, если сгибалась поверхность, то полосы такие. Вы видите, на них образуется нечто, электронно-микроскопическая картина, там больше отражение электронов или там вторичных электронов. То есть там что-то такое со структурой происходит. Ну, когда идем дальше, то видим, вот что происходит. Вы смотрите, получается, что вот это вот в вершине этих кристаллов или в вершинах гребней появляются кристаллы. Появляются кристаллы, в вершинах гребней там один кристалл, в вершинах там конуса один кристалл, а вот когда гребень, то там целая гряда кристаллов, да, как будто расческа какая-то вот такая, да, много кристаллов, они рядом друг с другом, вот такая гребенка такая получается. Ну, а если еще дальше облучать, то становится видно, что это вот один, там, а это второй, да, выступ, вот этот самый вершинка. Видно, что теперь вот эта луковица, она начинает сужаться, а в вершинах, вот там стрелкой показан, явно виден кристалл, который, вот кристалл, и здесь виден кристалл, да. Забегая вперед, я скажу, что эти кристаллы, если у нас весь этот самый, ну теперь уже конус состоит из, ну, вот из таких вот, да, вот так вот плоскости идут, то у этого кристалла плоскости идут вот так. То есть у него как бы восстанавливается, ну, кусочек пиролитического графита. Восстанавливается вот так, такая штука. Такие кристаллы появляются в разных случаях, но во всех случаях только тогда, когда в поверхности есть напряжение сжимающее. Я не буду вдаваться, вот, как это все происходит, но в общем обязательно должны быть сжимающие напряжения. Если в поверхности есть сжимающее напряжение, то каким-то чудесным образом, если это, вот, представьте себе обычный графит, то есть там кристаллы как угодно располагаются, да, и если какой-то кристалл располагается вот так, что вот, ну, как бы в пиролитическом таком варианте, когда вот слои вот так, то почему напряжение возникает? Потому что, ну, атомы туда, эти самые ионами вбиваются, да, там появляется лишний материал, и графит, как любой материал, хочет избавиться от этих напряжений. Так эти вбитые поверхностные атомы в глубине, они ходят как-то, да, и когда они попадают вот в этот самый кристаллик, у которого слои вот так расположены к поверхности, и создается здесь какая-то дислокационная петля, то, естественно, она выжимает эти слои, нижний слой, но ему смещаться некуда, а верхний слой смещается. Смещается, эта дислокация, так сказать, поднимается, а что в результате? А в результате один атомный слой вылезает над поверхностью. Но в кристалле в это время напряжение уменьшается, потому что ушел материал. Поэтому туда следующая порция атомов поступает, диффундирующая. Еще одна дислокация, еще один слой вышел. И вот так растет кристалл. Это получается и на плоской поверхности, ну, в соответствующих условиях. А вот здесь появляется он, этот кристалл. Нет других причин, только кроме поверхностного напряжения. Вот известно, что когда, если есть какой-то, ну, шарик, какой-то объект там, или, ну, это там какой-то квазицилиндр, конус, да, если его диаметр порядка микронов, то тогда силы поверхностного напряжения, они сравнимы с силами межатомного взаимодействия. То есть получается, что вот эта вот вершинка, она сжата. И раз она сжата, там появляется кристаллик. Вот это вот, это, я даже не понимаю, не могу объяснить, как он появляется, но он появляется. Ну, можно предположить что-то. Ну, в общем, и это мы видели неоднократно, что они появляются. Так что вот появляется вот такой кристаллик наверху, ну и он вот здесь уже видно, что он как-то вот так вот выпирает. Ну, дальше. Теперь вопрос, это вот некая схема, две схемы, показывающие, как там могут появиться лишний материал. И вот этот кристаллик. Вот слева это вот то, что я сказал, а справа это еще одна возможность, в принципе. Ведь мы же облучаем ионами, да, эту самую, вот этот самый выступ. Соответственно, атомы выбиваются в межслоевое это пространство, да, естественно, диффундирует вниз. Но когда диффундирует вниз, там может вот появиться вот этот слой, то есть дислокация, по сути дела. И тогда вот в силу вот многократного, так сказать, прихода атомов и рождением дислокации, вот может тоже появиться вот такой кристалл. мне кажется, вот это более вероятный левый, потому что появление таких кристаллов в конусах разных типов, ну, неоднократно мы видели. А то, черт знает, тоже может быть. Ну и дальше продолжаем облучать. А вот какая картина. В общем, эти холмы постепенно разрушаются. И видно, вот, ну, вам, наверное, плохо видно, что вы просто мне поверьте, что между этими выступами уже видна гладкая поверхность. То есть получилось так, что вот этот верхний кристаллик, в котором все вот это происходило, он уже, по сути дела, вот последний доживает. Да, и появился уже ниже лежащий кристалл, его плоскость появилась. Ну и еще немножко, если пооблучать, то в его плоскости, ну, то же самое, те же процессы пойдут. Вот. Ну а дальше, а что будет? Вот это поликристаллический был графит, да, то есть кусок графита, плоская поверхность, слои вот так располагаются, вот так все происходит. А вот мы в предыдущем докладе речь шла о том, что есть такие углеграфитовые нити. То есть в них тоже есть слои, которые несколько типов этих нитей промышленность делала, ну и сейчас делает. И вот в них вот эти самые графеновые слои идут различным способом. И это их делают так разными в зависимости от того, ну, для чего этого нужно. Больше всего использовался вот этот в первом ряду в середине, он like skin, лукообразная ситуация. Да, ее делали, и вообще для чего ее делали, для чего использовали, электропроводность у графита и теплопроводность, она очень высокая вдоль нитей, поэтому их использовали в разных ситуациях, в частности в термоядерных реакторах и так далее. И как это делали? Вот эти нити собирали вот, ну, в такие вот уже массивные куски, и вы видите вот в середине вот этот кубик или там прямоугольник, большая часть нити торчит наверх, а чтобы они не распались, их еще пронизывают в двух направлениях другого немножко типа нитей, и они занимают меньше места, и они не дают этому куску распасться. Ну вот справа это там вот как все это выглядит. Так вот, а что будет, если мы облучаем вот эти нити? Да? Значит, нить, вот так вот располагаются слои, да? И вот они вот так вот срезаны и торчат наверх. Да? То есть раньше мы облучали вот так нити, а теперь мы слои, а теперь мы облучаем вот так. И они, когда мы облучали вот так, все стало перпендикулярно. Да? Теперь, когда мы облучаем уже, так сказать, слои, которые стоят наверх, глядят наверх, а вертикально вниз уходят, у нас получается теперь вот эти вершинки, вы видите, они из слоев появляются перпендикулярных облучению. То есть получается, что обе вот эти самые два типа, ну, вот такое направление у графита и вот такое направление, так природа не терпит при ионном облучении ни то, ни другое. Она их друг в друга перегоняет, да, и в конце концов все аморфизует. Ну, дальше, ну, это то же самое. А теперь давайте пооблучаем, ну, вот как в предыдущем докладе было, вот эти нити, да, пооблучаем пооблучаем вот так, перпендикулярно оси. И что получается? Ну, эта картинка как раз группы ребят, которые изучали это дело. Вот это левая. Да, какая? Левая? Нет, правая. А левая это мы вот облучали ионами. У нас 7 КЭФ на самом деле, не электрон вольт СЭФ КЭФ, а здесь аргон. Да? Вы видите, если облучать вот таким вот образом, да, и в том и в другом случае происходит сильное распыление и очень большое количество выбивается атомов с поверхности, естественно. Теперь представьте себе, что у нас есть нить, да, мы понавыбивали много этих самых атомов. То есть нить лежит, вот верхняя ее часть, которая облучается, здесь атомы оказываются расположены далеко друг от друга. Они хотят сблизиться. Все то же самое, что в пиролитическом графите. Поэтому вот эта самая поверхность, она дробится, и каждая вот эта самая часть, да, она изгибается и поворачивается наверх. Все. Все они повернулись, и получилось вот то, что это то же самое, что получалось у того графита. Видите, вот отдельные вот эти вот самые повернутые слои. Вот так. А что теперь происходит, если мы облучаем 30 кэф? Вы видите, энергия ионов гелия. Это такая энергия, когда ионы пролетают глубоко и создают уже дефекты, максимум дефектов, на глубине своего пробега. То есть поверхность, она оказывается не сильно разрушенной, но в поверхность вбиваются атомы, и поэтому здесь получаются напряжения не растягивающие, а сжимающие. А теперь, если нить, и у нее сжимающее напряжение, то как снять напряжение, если у вас вот сжато все, да? Единственный вариант сделать так, чтобы напряжение спали, уменьшились, нужно вот это расстояние, где напряжение, увеличить. А как ее увеличить? Выгнуть наверх. И вот появляется одна выгнутость, другая выгнутость, третья выгнутость. И вот эти уже выгнутости, да, они идут вдоль нити. И здесь в вершинах вот-вот появится тоже кристалл. Вот-вот. Ну, пока не появились. Так, ну и conclusion, это, по сути дела, то, что я сказал. Да? Так что получается такая ситуация, что графитовая вот эта вся структура, если у нас есть пиролитическая структура, она превратится наоборот, вот так будут слои, потом эти слои будут иметь тенденцию опять превращаться в плоскости и так далее. И так, пока этот графит не превратится в поликристаллический графит с самым разным расположением всего. В общем, полный пока беспорядок не будет. Все, спасибо за внимание.
Давайте поблагодарим. И у нас есть время, может быть, на 1-2 коротких вопроса.
Эрозия происходила, которая оценивается коэффициентом распыления. Да? Вот в ваших экспериментах оценивали вы там такое расслоение, что, может, эти хлопья вообще улетали, когда вот на пиролитическом графите в первом цикле? Может, там аномально, сверханомальный как бы коэффициент распыления происходил? Не смотрели?
Начинается с того, что химическое распыление. После этого уменьшения, когда там водород выйдет, химическое распыление кончается, дальше начинается подъем, то, что называется radiation and mass sublimation. Суть дела в том, что если на поверхности распыляется на поверхность, распыляется поверхность, слабо связаны с поверхностью, поэтому они легче соединить. Еще, если большая плотность температуры, если увеличивать, то оказывается, что вакансии, когда температура 1700 Цельсия, что-то в этом пике дальше, то вакансии, которые на поверхности идут, образовываются, они большой частью деформируют глубину. И в глубине образуется пористый слой, пористый, совершенно пористый. А эти атомы, которые порист, что значит? Вакансия пришла, значит, атом, значит, отсюда, если вакансия сюда пришла, значит, атом отсюда сюда пришел. И с этим пористым слоем атомы выходят на поверхность, тоже участвует в распылении. Поэтому в этом sublimation еще вот, не знаю, как назвать этот процесс, когда распыление происходит и поверхности, и из глубины. То есть еще один подъем распыления. Это все мы делаем.
Леонид Богданович, у меня к вам тот же вопрос. Вот вы говорите, какой-то кристалл сверху образовался. Вопрос вот какой. Меняется ли аллотропный вид вот этого углерода в этом кристалле, в массиве, или все это остается все-таки пиролитическим графитом? Нет, есть однозначно электронная структура материала, на которую я могу четко ответить. Пиролитический графит по положению там пи-плазмона, по положению пи плюс сигма плазмона. Я четко могу сказать, что это за вид графита. Вы делали такие эксперименты? Все я сделаю для вас тогда. Угу. Не, ну это интересно же. Нет, ну это самый надежный метод. Ну, понятно.
Все, давайте поблагодарим докладчика еще раз. Спасибо. Так, и следующий доклад у нас онлайн. Максим Александрович Маховиков. Оптико-структурные свойства кремния, гипердопированного индием и мышьяком. Эффект электронно-лучевого отжига. Максим.
I'm here. You can. Okay. Good day, everyone. Oh, what? What is? Good day, everyone, and thanks for coming. I'm very happy to take part at this conference. And at first, I'm sorry, I have a very short presentation, and I am started. The title of presentation is Optical and Structural Properties of Silicon Hyperdoped with Indium and Arsenic, the Effects of Electron Beam Annealing. The study were conducted in the Institute of Applied Physics Problems, Minsk, Belarus, in collaboration with group of Belarusian State University, Friedrich Schiller University, Jena, Germany, and Institute of High Current Electronics, Tomsk, Russia. As you know, silicon is a semiconductor with an indirect band gap at low quantum efficiency of interband radiative recommendation, which complicate its use in optoelectronics. Silicon as a material for solar cells transmits the infrared part of the solar spectrum in the range of from 1.1 and to 3 micrometer, which is about 30% of the total solar energy flux. Moreover, silicon photodetectors are intensive to the 3 main bands of fiber optic communication: S-band, C-band, and L-band. Replacement of electronic intra-chip and inter-chip switching with optical ones promises a huge gain in silicon microelectronics. In our previous works, we reported a creation of light-emitted structures based on direct band gap, A3B5 and A2B6 nanocrystals, such as gallium stibum, indium arsenic, zinc oxide, tin oxide, and others nanocrystals in a silicon matrix, as well as of photodetector structures based on silicon doped with chalcogens using of high fluency ion implantation. This group 3 and 5 or 2 and 6. Followed by subsequent thermal and laser annealing. In present work, we use of electron beam pulse annealing. This will be considered for the first time to form a layer of silicon hyperdoped with indium and arsenic impurities. we assume the silicon hyperdoping with indium and arsenic impurities will increase the level of absorption by silicon in the near infrared range. Such hyperdoped layers are potentially can be used for efficient infrared range photodetectors compatible with the silicon complementary metal oxide semiconductor. Initial samples were cut thermally oxidized silicon of thickness of 14 nanometer on the silicon and then implanted arsenic and indium ions at high temperature. We use regimes of implantation and annealing we can see on this slide. We use pulsed electron annealing with melting and without melting. The Rutherford backscattering spectroscopy, transmission electron microscopy, and Raman scattering spectroscopy were used to evaluate the depth distribution of embedded impurities and structure phase transformation within implanted layers. At the moment we are in the very beginning of the study, and this report does not consider the optical characteristic of the obtained structures. This investigation of optical and luminescence properties of silicon implanted with indium and arsenic with subsequent electron pulse annealing is a subject of future investigation. This slide shows concentration profile for indium and arsenic impurities calculated from array-based data for as implanted and annealed samples. We can see the implantation results in a shift of concentration profile to the surface in comparison with simulated profile. We can see the impurity loss during implantation is about of 11 and 12% for arsenic and indium impurities respectively. Pulsed electron annealing results in significant redistribution of indium and arsenic atoms. In the case of the pulsed electron annealing without melting, this one profiles. The impurity loss is not significant. 4% for indium and about 7% for arsenic impurity. The highest impurity loss, about 50%, were registered for arsenic impurity in case with melting, this one. According to TM data, pulsed electron annealing results in the formation of dislocation time secondary defect region located along the crystallographic planes 001. We can see on the slides the size of secondary defects is from 100 nanometer to micrometer. And on this image at the energy density 10 joule per square centimeter, we can see the contrast of light at dark spots indicates impurity redistribution with the sample and the formation of very density zones. The formation of indium arsenic nanocluster is not observed. On this slide, presented Raman data results. The intense bands at 520 corresponds to a signal from the silicon substrate, and the two bands, this one and this one, are attributed to TO and LO phonons of indium arsenic. The highest intensity of indium arsenic bands was observed for the sample without melting. It's number 1. After pulsed electron annealing with melting, number 2 and number 3, signal from crystalline indium arsenic was also obtained. In conclusion, at first, the impurity loss during implantation is about 11 and 12% for arsenic and indium impurities, respectively. Subsequent pulsed electron annealing results in a significant redistribution of indium and arsenic atoms. The highest impurity loss, about 50%, was registered for arsenic. In the case of electron beam annealing with melting. The analysis of TEM images reveals the formation of layer of dislocation type secondary defects located along the crystallographic planes 001. Raman's spectral data prove formation of indium arsenic nanocrystals in the implanted silicon after pulsed electron beam annealing. The highest signal we can register it in the case annealing samples without melting. And thank you very much for listening, and I hope that my short presentation you found it interesting. Thank you very much.
Please thank the speaker. Any questions?
Thank you very much for your presentation, but can you explain the occurring in your Raman spectra, the signal from indium arsenic, and you cannot see this one in the TM pictures?
TM pictures? What is? Maybe you asked questions on Russia, but thank you.
Вы видите ТО и ЛО моды на рамановских спектрах, вы не видите ничего в микроскопии, ни по дифракции, ни по расу. Как объясняете?
Я объясню сейчас, если можно, на русском. Да, действительно, рамановские спектры показывают наличие фракции, кристаллической фракции индиумышика, но на самой микроскопии мы этого не видим, к сожалению. Это можно объяснить тем, что наночастицы индиумышика имеют очень маленькие размеры, которые невозможно зафиксировать микроскопом. То есть очень маленький их размер, но они есть.
Спасибо. Но вы тогда можете сравнить ТО и ЛО моды и по этим модам определить размер. Вы это делали?
Нет, к сожалению, не делал. Это в будущем. Тут маленькая оговорка. Доклад мой действительно очень короткий и недополненный именно оптической частью и расчетом некоторых составляющих из микроскопии и элементного анализа. Но пока что вот то, что есть, могу представить. К сожалению, так вот получилось.
Так, еще вопрос.
такой вот вопрос просто для образования. Вот ваша терминология impurity loss. Что вы имеете в виду?
Потери примесей.
Потери по сравнению с чем?
Ну вот смотрите, например, по РБСу, ну, профиль я рассчитывал из РБС-спектров. Потери примеси после имплантации я оценивал по сравнению с профилями из СРИМа. Вот. А последующие отжиги с расплавлением или без расплавления я оценивал уже по спектрам, которые, ну, по профилям, которые были рассчитаны после имплантации. То есть вот именно так.
А вот на этом рисунке чем отличаются два графика слева и справа? Вот у вас непонятно из презентации.
Согласен, немножко непонятно.
Очень
Сейчас
мелкий текст, и вы не комментируете. Чем отличается левый и правый?
Левый представление профиля распределения примеси после имплантации и после отжига без расплавления, а справа это с расплавлением, но при двух различных энергиях отжига.
Могли бы поставить просто слова с расплавлением, без расплавления. Все было бы.
Ну, я так и поставил. Тут ну да, тут без расплавления, а тут, ну да, согласен. Все, спасибо.
Еще вопросы? Давайте поблагодарим докладчика еще раз.
Спасибо большое.
И у нас последний доклад Екатерина Корнеева. Micromechanical testing of Swift heavy ions irradiated materials.
I'm honored to be at this conference and present my work, micromechanical testing of the Swift heavy ions irradiated materials. Up to date, there is a need for Generation 4 nuclear systems for new constructive materials that will satisfy high requirements of structural stability under high temperature and high radiation dose. And there are two areas of focus. One of them is the research for materials for inert matrices. And there are different ceramics in this group, like nitrides, carbides, and so on. And the second group is materials for fuel claddings. And in this group, there are oxide dispersion strengths in steels, reduced activation ferritic martensitic steels, and high entropy alloys. So in my work, I will tell you about two materials from each group. First one is oxide dispersion strengths in steel. In the structure of such steel, there are nano-sized particles based on yttrium oxides. Here you can see the typical microstructure of such steel. And these oxide particles can act as barriers for dislocation glide. The boundary between particle and matrix can be efficient trap inside for point defects and helium. And because of that, ODA steel demonstrate high temperature creep resistance and high resistance to void and helium swelling. And that's why ODA steel are considered as material for fuel claddings. And other material is silicon nitride. It has high resistance to neutron radiation and chemical stability. It is stable chemically at high temperatures. So that's why this materials is considered as material for inert matrix fuel host. Despite that materials are quite stable under neutron radiation and radiation by low energy ions that are common used in radiation material science. In reactor, there are different kinds of radiation, and actually the most interesting and less studied is fission fragments radiation. Because of high levels of electronic excitation during this kind of radiation, it can be crucial for dielectric materials. And here you can see on the right picture the latent tracks in the pyrochlor particle in ODS steel, and at high dose, this effect can lead to amorphization of the material. And you can see here the amorphous part of the irradiated aluminium 203. This structure evolution may cause a drop of mechanical properties, and the aims of the present work are simulate fission fragments radiation by swift heavy ions and estimate the change of mechanical properties of radiated materials by non-annotation based methods. So let's start from ODS steels. We study two kinds of ODS steel. First one is chromium-16 ODS steel from Bochvar Institute. And this steel have pyrochlor particle and Y2TO5 particle in its structure. The mean size is about 10 nanometer, but actually there are quite big particles up to 100 nanometer. And also there are a lot of carbide particles in the structure, and they are also quite big. Another ODS steel is Euroferro ODS steel, and here the particles are presented by yttrium oxide, and they are very small, several nanometers in diameter. And here you can see the biggest particle that we can observe. It is about 10 nanometer. Also, there are a lot of carbide particles, like in chromium-16. But their size are smaller, and actually the microstructure of the Euroferro ODS is more homogeneous than in chromium-16. So these steels were radiated on IC-100 cyclotron in Joint Institute for Nuclear Research in Dubna. And here you can see the table with radiation parameters. From the previous work, we know that threshold stopping power for latent track formation in pyrochlor is in the range from 7.4 to 9.7 keV per nanometer. And at the last column, you can see stopping power for different kinds of particles that correspond to these ions. So these steels were radiated in two modes. First is below this threshold stopping power, so there is no effect on oxide and carbides. And the second mode is above this value. The latent tracks form in oxide particles and carbides. And starting from the fluence of 2 multiplied 10 to 12, the particles become amorphous. Here you can see amorphous particle in chromium-16. And as for Eurofer, actually we didn't see amorphous particle in the structure because they are very small. But we expect that some damage also can be in these particles because XRD analysis from irradiated powder of yttrium oxide shows that amorphous part increases with fluence. So now I turn to mechanical properties estimation, and it is known that non-indentation is the best method to estimate mechanical properties on micro scale. But actually there are some disadvantages on this method because there can be some kind of size effects, and problems with non-uniform deformation during this process. So in order to avoid these problems, it is usually modern technique to estimate mechanical properties to test microsamples. And in our work, we choose micropillar compressions. It is a good method, but it's still an open question if it's okay for our ion-radiated materials because of non-homogeneous damage region after ion radiation. So we have two kinds of damage after shear radiation. First, through elastic collision. Here you can see profiles of argon and xenon ions, and the maximum damage is at the end of the ion path. And we can see that up to 4-5 micron, the damage is almost the same. And the most important for us in the case of ODS steels is damage through electronic energy loss. And here you can see ionizing energy loss profile of xenon ions in pyrochlor. And let's look at this picture in detail. So this red symbol is related to threshold stopping power for latent drag formation. Above this value, we observe latent drags in oxide particles, and their sizes slightly decrease with depth. But we can see also that up to 4-5 micron, this region is almost the same, and actually our particles are all in the same structural state. So taking this in account, we use some pillar height of 4 micrometer, and here you can see at the top the stages, different stages of fabrication of this pillar. It was made by focused xenon ions. And the height was, as I have said, 4 micron, and the diameter was 2 micron. Here you can see a laminate standard assembly that was established in a camera of scanning electron microscope, and here is a diamond flat punch tip with a 2 micron diameter. And also before compression, we did an express BSD analysis to make sure that there are a lot of grains inside one pillar. And I have problems with that video, but I want to show you some examples of how the deformation process takes place. Yes. Now you can see the video. This is the initial sample, non-radiated chromium-16. You can see shear bands during deformation. And now it is irradiated chromium-16. Here you also can see shear bands. And this is Eurofer, they're still in initial state, and the deformation process is a little bit different from for chromium-16. There is no evidence shear bands. This materials is more strength. And the same situation is for irradiated Eurofer. So we think that this difference between chromium-16 and Eurofer steels is because of different microstructure, different grain size. So thank you very much. And now using these formulas, we got stress strain curves for our samples. And here are the results of yield strengths dependency on fluence. And you can see that there is a strengthening up to 10 to 12%. And actually, I want to pay your attention that argon radiation radiation sample has almost the same value of strengthening as xenon radiated sample. So actually this is in a good agreement, this result is in a good agreement with the previous results that we obtained with classical nano-indentation. And we think that the strengthening of the steel is because of point defects and not because of structure of oxide particles. So now I turn to silicon nitride. Here is its initial microstructure, and it was radiated on IC100 and U400 cyclotrons in Jinner Dubna, and also on DC60 cyclotron in INP in Kazakhstan. And we know that threshold stopping power for latent track formation is about 15 kV per nanometer. So this materials also was irradiated in two modes by argon and krypton ions below this critical value, and by xenon and bismuth ions above this value. Briefly about change in microstructure. So here you can observe latent tracks in the structure, and with fluence up to 10 multiplied 10 to 13, we can observe individual latent tracks in the structure. And starting from the fluence of about 10 to 14, there is complete amorphization of the material. And also on the surface, we can observe such a damaged region of radiated sample. And for mechanical properties estimation, we use standard nano-indentation. Here you can see the result. This is variation of relative changes of the hardness in silicon nitride against DPA. So you can see that argon radiation doesn't have any visible effect on hardness. At the top right corner, you can see a low displacement curve for argon irradiation, and there is no difference between unradiated and radiated sample. Krypton radiation lead to about 5% hardening due to point defects induced from elastic collisions. And here you can see low displacement curves, and this dot curve is for unirradiated samples, and you can see that curves for irradiated samples, they turn to the left, and that is an indication of the presence of residual stress, compression residual stress. As for bismuth and xenon irradiation, these low displacement curves are very similar. So there are two stages. The first stage is at fluence up to 5 multiplied 10 to 12. The low displacement curves turn to the left. So it's compressive residual stress. And starting from the fluence of 10 to 13, these curves turn to the right. So some kind of stress relaxation take place. Okay. As for hardness, so there are also two stages for xenon and bismuth radiation. At first stage, hardness increases due to point defects formation. At the second stage, hardness decreases. And this there is an equation between hardness and covalent bond number per unit area. And because of the amorphization, this Na decrease, and that's why the hardness decreases. Also, we make some observation of post-indentation material, and we see the increase of fracture toughness up to several value. So that is summary. I didn't read it. I won't read it. So thank you very much for your attention.
Okay, thank you. Any questions?
Екатерина, если можно, я на русском задам вопрос. Смотрите, вот вы там показывали пилоры, они довольно крупные, да, это 20 микронов, в глубину, наверное, тоже порядка 60.
Нет, 4 микрона в высоту.
4 микрона в высоту, диаметр у них где-то 20.
2.
Да? 2. Замечательно. Ну, все равно достаточно крупные, но типа размера одного зерна получается. Вот я по сталям, конкретно по сталям спрашиваю, которые у вас вот эти 13 хром или 16 хром до сталь и КП-4, вот это корейская сталь. Вопрос следующий. Вот вы сказали, у вас там два эффекта, высокоэнергетичные ионы. У нас есть эффект неупругого рассеяния, ну, от неупругих потерь энергии, от упругих потерь энергии. По вашему мнению, какой из них вносит наибольший вклад в то, что мы видим в разрушении материала? И второй вопрос. Вот в случае российской стали, российского производства, вот эти частицы, они довольно крупные, как вы заметили. Порядка там до 200 нанометров. Опять же, я на глаз ориентируюсь по картинкам. Причиной разрушения являлись возникшие в материале радиационно-индуцированные дефекты, или же причиной разрушения служили сами частицы, поскольку их размер, он уже подпадает под критерий зарождения трещины в материале, тем более если у вас решетки не когерентные, а вы вроде указываете, что это частица именно И3-2, титан-2О7, значит, она имеет определенную кристаллическую структуру, она не когерентна, она может служить сама по себе трещиной в материале. То есть вот как вы вот эти вопросы рассматриваете?
Мы считаем, что основной вклад вносят упругие, господи, не могу переключиться на русский. Мы считаем, что основной вклад от упругих соударений и частицы не влияют на механические свойства. В случае вот стали хром-16, на самом деле это первое поколение этих ОДС-сталей, частицы очень крупные. Вот, и когда мы делали этот анализ Доры, вот здесь видны такие серые области. Вот, вероятно, это как раз-таки какая-то частица карбида или оксидная частица. И, вероятно, вот этот вот деформационный процесс, который такой очень, показывает, что вещество, что эта колонна довольно хрупкая, она связана с тем, что там как раз-таки эти частицы крупные есть внутри. То есть такая неоднородность, она, скорее всего, влияет на это.
То есть вы не анализировали поперечное сечение вот этого слома, чтобы убедиться, разрушение произошло внутризеренный характер был, межзеренный или по частице?
Ну, пока еще нет, это в планах.
Еще вопросы? Все, тогда поблагодарим докладчика еще раз. И на этом наша секция закрывается. Вот Владимир Иванович что-то хочет сказать.
Сейчас начнется сессия. Ну, я предлагаю вам слегка подкрепиться, выпить чаю, съесть бутербродики на первом этаже. Значит, еще раз повторяю, завтра у нас экскурсия для всех. 2 автобуса к 2 часам подъедут к отелю. Значит, после обеда выходим. Бесплатно. А погоду зачем? Мы приедем в Ростов на автобусе, там будем ходить по Кремлю. Потом сядем в автобус и поедем на ужин. Вопросы есть? Ужин? Ну а как же без ужина-то? Здесь в отеле будет ужин. А товарищеский ужин будет у нас в четверг. А где, я вам скажу только в четверг. 18:00. Так что никто не манкирует.